Imagine attempting to hover perfectly still in midair while simultaneously ejecting water from a garden hose in random directions. Physics dictates that such a feat is fundamentally impossible. The momentum carried by the water should send you tumbling off course. Yet, astonishingly, right now, in the dark expanse between the worlds, an object roughly the size of a city block is executing precisely that feat. This enigmatic entity, known as 3I Atlas, has arrived from interstellar space and is demonstrating behavior that sharply contradicts our most basic understanding of how objects move through the cosmos. This object is actively venting material just like a typical comet, expelling gas and dust into space. But despite this apparent activity, it somehow avoids the acceleration that physics predicts should be an inevitable consequence of such outgassing. Engineers refer to this phenomenon as the rocket effect, a force typically responsible for altering the course of comets and other small bodies, and which has historically always been detectable and predictable. The fact that this effect appears absent in this case raises profound questions. Tonight, we will delve into why this single anomaly could potentially mark humanity's first encounter with technology not of terrestrial origin. Join us as we explore how 3I Atlas might be providing the most compelling evidence for extraterrestrial intelligence ever observed. Its behavior challenges the very principles of celestial mechanics and invites us to reconsider what is possible beyond Earth, and perhaps beyond our planet's understanding. Part 1. The impossible object. At first glance, 3I Atlas is venting gas and dust into space in a manner indistinguishable from a typical comet. It appears to be actively shedding material, yet its trajectory remains unwavering, defying the laws of physics as we have understood them. Visualize this: an icy asteroid hurtling through the dark void of interstellar space, sporadically firing microscopic jets in unpredictable directions. According to all established principles of orbital mechanics, these tiny bursts should function like thrusters, imparting small but measurable nudges to its movement, altering its course in ways that precise calculations can detect. However, this interstellar visitor seems to be defying one of the most fundamental principles governing spaceflight. To clarify this perplexity, let's define some key terms in just 20 seconds. When astronomers observe objects moving through space, they differentiate between two types of motion. One governed solely by gravity, the natural, predictable dance of celestial bodies following Newton's laws, and another, what scientists call non-gravitational acceleration, or NGA. Think of NGA as the tiny, persistent shifts in speed and trajectory caused by forces such as outgassing steam from sublimating ice, or the gentle push exerted by sunlight radiation. For most active comets, these forces are as reliable as clockwork. Gas escapes from the nucleus, transfers momentum, and causes the object's path to subtly shift over time. This is classic rocket science in its purest form. Outgassing produces a measurable thrust. But here's where 3I Atlas becomes truly mysterious. The Hubble Space Telescope has captured stunning images of its shroud of gas and dust, the so-called coma, surrounding the object. Meanwhile, the James Webb Space Telescope has analyzed its chemical fingerprint with unprecedented precision, revealing detailed insights into its composition. Observatories such as Gemini South and the Very Large Telescope have tracked the development and evolution of its tail structures over weeks and months. Every instrument pointed at this object confirms one fundamental fact: it is actively venting material into the surrounding space. Yet when astronomers perform meticulous calculations, fitting orbital models to months' worth of positional data, they find no signature of the expected acceleration. The non-gravitational push that should result from the escaping gas remains elusive. It is either absent or so minuscule that it falls at or below the detection limits of current measurement techniques. In fact, current orbital solutions have yet to report a definitive, peer-reviewed detection of non-gravitational acceleration. Instead, they only establish upper limits, bounds within which the force could be present but remains undetectable with current technology. This situation is akin to radio silence in the face of what should be a clear, unmistakable signal, leaving scientists pondering whether the object is truly defying the laws of physics or if their instruments simply aren't sensitive enough to detect the subtle forces at play. This phenomenon is not merely unusual. Within the realm of comet physics, it teeters on the edge of what we deem physically plausible, bordering on the impossible. To illustrate, imagine observing a balloon slowly deflate while expecting it to drift lazily across the room. Instead, you see it hovering motionlessly, seemingly suspended in midair. That's the kind of paradox presented by this object. Telescopic observations reveal gas flowing from the entity with its emissions favoring certain directions, yet paradoxically, it shows no measurable drift, no gentle push or shift that one would expect from a leak or outgassing. This defies fundamental physics, which predicts that escaping gases should impart a corresponding momentum, nudging the object in the opposite direction. From this perplexing situation, two interpretations have emerged, each representing a radically different worldview about what we are witnessing. The first perspective maintains that we are observing a natural phenomenon, albeit an extraordinarily unusual one. Perhaps it's a colossal nucleus capable of absorbing or counteracting the recoil from its outgassing without any noticeable change in trajectory. An almost implausible feat. Alternatively, it might possess an exceptionally symmetric pattern of outgassing, with jets firing in perfectly balanced forces canceling each other out so precisely that the overall motion remains static. Such a scenario, while extraordinary, is rooted in natural physics and the known behaviors of cometary bodies. The second interpretation, however, ventures into more speculative and controversial territory. It whispers of artificial stabilization. What if some unknown entity or technology is actively suppressing the object's drift? What if it's a deliberate attempt to minimize detectable movement, maintaining a steady position in space despite active emissions? This idea, while not yet mainstream science, has gained attention in research papers and scientific forums, sparking debate and curiosity. It's important to recognize that this line of thinking pushes beyond conventional understanding, challenging the assumption that natural processes alone can account for such phenomena. This second possibility is rooted in the observations of theorists and commentators who are willing to stretch the boundaries of accepted science. It's not yet part of the consensus, and it's certainly not established fact. Still, when considering that this object, designated as 3I Atlas, stands only as the third confirmed interstellar visitor in human history, a rarity that spent millions of years journeying through the vastness of interstellar space before arriving in our neighborhood. Every piece of data takes on immense significance. Each detail might hold clues to its origin, nature, and purpose. The stakes are astronomically high. This object won't be with us forever. As each day passes, it grows fainter, retreating back into the depths of interstellar space, carrying with it the secrets of its formation and history. Our window to decipher its mysteries is rapidly closing. Before 3I Atlas disappears into the cosmic background, leaving us with more questions than answers, we must act swiftly. The limited time frame demands careful, precise investigation, distinguishing between what our instruments have directly measured and what remains speculative or interpretative. The facts we have are startling. Visible activity detected through telescopes without any corresponding measurable effects on its trajectory. This contradiction opens profound questions. Are we witnessing exotic physics beyond current models? Or could this be evidence that we are not alone in the universe, perhaps encountering some form of artificial intervention? The timeline of its discovery has already presented us with additional puzzles. An unexpected early brightening that caught our attention, and hints that the object might be modulating or slowing its activity in ways that contradict our existing models of comet behavior. The story of 3I Atlas isn't a single event but a gradual unveiling, beginning with months of meticulous sky surveys. The earliest images taken during routine recovery efforts in May 2025 show only a faint point of light, just another indistinct speck among trillions in the universe. It was only on July 1st, 2025, that something unusual emerged from the data, prompting astronomers worldwide to pay closer attention. The Atlas telescope in Chile, a highly automated sentinel meticulously designed to scan the night sky for potentially hazardous asteroids, unexpectedly recorded something extraordinary. This wasn't merely about what it observed, but rather how swiftly this object traversed the cosmic stage. Its rapid movement defied conventional expectations, prompting initial calculations that indicated a hyperbolic trajectory, a clear mathematical signature of an object not gravitationally bound to our sun, but passing through our solar system on a fleeting, unbound journey. Within a matter of days, confirmation arrived from observatories scattered across the globe, cementing the fact that humanity had identified its third confirmed interstellar visitor. The approach vector of this enigmatic object added yet another layer to the unfolding mystery. It appeared to emerge from the direction of the galactic center, specifically from the constellation Sagittarius, a region densely packed with stars where celestial chaos makes early measurements akin to trying to thread a needle in a storm. The stellar crowding complicates initial observations. The sheer density of stars means that early data points are often subject to rapid revision as more precise information becomes available. Tracking an interstellar visitor against such a crowded stellar backdrop is a formidable challenge. Every photon counted, every data point matters profoundly, because in astronomy, context is everything. The particular numbers, distances, velocities, trajectories, are the key to understanding this visitor's story. As the object approached our sun, it was projected to reach its closest point around the 30th of October 2025. At that time, 3I Atlas would come within approximately 1.4 astronomical units, that is, about 200 million kilometers or roughly 1.5 times the distance from Earth to the Sun. From our vantage point on Earth, it would never venture closer than between 1.7 and 1.8 astronomical units, a comfortable distance that poses no threat to our planet. This object is emphatically not a danger, no collision risk, no need for planetary defense protocols. Yet, despite its benign trajectory, the scientific significance of such an object often diverges from its safety profile. Early photometric observations painted a picture of swift transformation. Soon after its initial detection, astronomers reported a significant increase in brightness, a telltale sign of developing activity. The object began exhibiting a characteristic coma, an envelope of gas and dust, and actively venting material into space. Such activity is typical of comets as they heat up, but the details behind these brightness changes warrant cautious interpretation. Precisely how much the brightness increased, and whether this was solely due to sublimation of frozen gases under solar heating or influenced by viewing geometry and the expanding coma, remains under detailed investigation. Multiple datasets are being scrutinized, but until they are fully analyzed, rushing to headlines about a sudden, dramatic brightening would be premature. Scientific verification demands patience and careful validation. One of the most iconic images of 3I Atlas emerged from the Hubble Space Telescope on July 21st. It provided our first unambiguous glimpse of the object in action, a distinct sun-facing plume extending from the nucleus, a clear marker of active outgassing directed precisely toward the sun. This plume demonstrated that material was escaping the object's surface, driven by solar radiation and sublimation processes. Adding to the intrigue, faint features resembling an anti-tail, material pointing toward the sun rather than away from it, began to appear in the data. These ghostly structures, which defy the typical tail behavior of comets, evolved over the subsequent weeks. By late August, observations from the Gemini South Observatory revealed a more conventional tail structure, with dust being swept away from the sun by radiation pressure and solar wind. This transition from faint anti-solar features to a more familiar tail pattern suggests complex interactions between the object's activity, its rotation, and its surface properties, offering valuable clues to its nature and behavior. The transition from the object's unusual anti-tail features to a more conventional tail development presents a captivating puzzle that invites us to consider its rotation, surface characteristics, and the intricate dynamics of its ejected materials. To grasp these phenomena without drowning in complex technical jargon, let's take a moment to clarify what tail geometries reveal about such objects. An anti-tail, contrary to what one might initially suspect, isn't a sign of backwards physics or alien propulsion systems. Instead, it's primarily a matter of perspective and the natural laws of orbital mechanics. When Earth, the comet, and the Sun align in particular configurations, we observe dust particles that were expelled from the comet's nucleus weeks or even months earlier. These particles, having spread out along the comet's orbital path over time, create a visual illusion. It appears as if the dust is pointing toward the Sun. However, in reality, this is just the visible manifestation of a much larger debris sheet, material that has been released earlier and is now distributed along the comet's orbit. This phenomenon, while unusual at first glance, is entirely natural and has been observed in many comets within our own solar system throughout history. The timing and changes in these tail features, especially in an object like 3I Atlas, add nuanced layers to our understanding of its behavior, each detail piecing into a larger cosmic puzzle. Now, considering how dramatic these activity patterns are, producing plumes and tail structures that are visible with our most powerful telescopes, the core question resurfaces with even more urgency. Where is the non-gravitational acceleration that should accompany such vigorous outgassing? In other words, if this object is actively releasing material, why isn't it being noticeably pushed by its own emissions as physics would predict? This is the fundamental tension. Visible activity suggests a force, yet the expected dynamical response is conspicuously absent. This paradox is what makes the situation so intriguing. In astronomy, when the anticipated effects, such as the object's movement shifts, fail to materialize despite clear signs of activity, it often signals that something unexpected and potentially groundbreaking is at play. This discrepancy, the visible signs of outgassing without the corresponding dynamical influence, sets the stage for everything that follows in our exploration. To better understand this, imagine a skateboarder riding along holding a water bottle that slowly leaks. The water escaping from the bottle exerts a gentle, continuous push in the opposite direction of the leak, gradually nudging the skateboarder backward. This simple example is a scaled-up analogy of the rocket effect in space. The same principle underpins how comets and asteroids are subtly nudged by the gases and dust they eject, an effect that influences their orbital paths over time. However, measuring this tiny push from millions of kilometers away demands extraordinary precision. Astronomers utilize high-accuracy astrometry, meticulously tracking the position of such objects over weeks and months, seeking the faintest deviations from a purely gravitational orbit. They develop comprehensive mathematical models that take into account all known forces: the sun's gravitational pull, perturbations from planets, the effects predicted by Einstein's theory of relativity, and then analyze the residual discrepancies. These residuals, if any, could indicate non-gravitational influences like outgassing. Imagine trying to determine whether a distant ship is being gently pushed by a breeze by observing its movement through a telescope against the backdrop of stars. The numbers involved are so tiny that they are almost beyond comprehension, yet they carry profound implications. For instance, our previous interstellar visitor Borisov, detected in 1919, exhibited a non-gravitational acceleration consistent with typical outgassing behavior. An example of how these measurements, though delicate, can tell us a lot about the physics governing small bodies in space. When scaled to a distance of 2 astronomical units from the Sun, the tiny non-gravitational acceleration observed on the interstellar object known as 3I Atlas registers approximately 3.8 times 10 to the negative 7th meters per second squared. While this figure sounds minuscule, almost negligible, its significance becomes apparent over extended periods. Months of meticulous observation reveal that even such infinitesimal accelerations can gradually accumulate, leading to measurable shifts in the object's orbital path. These tiny pushes, seemingly insignificant at first glance, can, over time, alter the trajectory enough to be detected and analyzed, providing crucial insights into the forces acting upon these distant travelers. In stark contrast, the first confirmed interstellar visitor, the enigmatic object called Oumuamua, showcased the opposite end of the spectrum. Despite exhibiting no detectable gas or dust emissions, no visible signs of outgassing, it demonstrated a much larger non-gravitational acceleration, approximately 4.9 times 10 to the negative 6th meters per second, squared at a distance of 1 astronomical unit from the Sun. This value was about 30 times greater than that observed for Borisov, the previous interstellar comet. The puzzling aspect of Oumuamua was precisely this: it appeared completely inactive. Telescopic observations revealed no detectable jets or tails, yet it seemed to be subject to a substantial push, an invisible force, mysteriously accelerating it through space. This paradox of an inert, seemingly dead rock being propelled by unseen forces ignited years of intense scientific debate. Researchers grappled with understanding what could produce such acceleration without the usual signs of outgassing or other activity. This challenge to conventional models pushed the boundaries of existing theoretical explanations, forcing scientists to reconsider assumptions about what might be driving such forces in objects that show no visible signs of activity. To put this into perspective, consider the well-studied comet 67P Churyumov-Gerasimenko, which was exhaustively examined by the European Space Agency's Rosetta mission. Spacecraft instruments delivered direct measurements that confirmed the predictions of orbital mechanics. Outgassing from sublimating water ice and carbon dioxide creates measurable thrust vectors. These jets produce forces that alter the comet's trajectory in predictable, quantifiable ways. Mission planners meticulously accounted for these forces when navigating the spacecraft and positioning instruments, using the data from Rosetta to calibrate their models of comet activity. Rosetta's detailed observations provided a ground truth, a baseline understanding of how active comets behave and how their outgassing drives their movement through space. This understanding underscores the critical importance of symmetry in the outgassing process, especially when examining anomalies like Oumuamua and Atlas. Imagine, for instance, performing the water bottle experiment again, but with leaks emanating in multiple directions. If the leaks are perfectly balanced, the forces cancel each other out, and the object remains stationary despite vigorous activity inside. Scaling this up to a rotating comet nucleus with several active regions, one can envision scenarios where intense outgassing occurs, yet the net thrust remains minimal. The key point is that the net acceleration is not necessarily zero, but so close to zero that the object appears nearly motionless in terms of its trajectory, a condition that would be quite remarkable in itself. Achieving such perfect or near-perfect cancellation requires an extraordinary level of symmetry in outgassing patterns, surface activity, and jet orientation. This brings us to the current status of 3I Atlas within the realm of unusual celestial objects. Spectroscopic observations confirm that it possesses a coma, an envelope of gas and dust, rich in carbon dioxide indicating active outgassing. Visual imagery shows that its tail structures and plume features are evolving over time, suggesting ongoing activity that responds to solar heating. Yet despite this apparent activity, orbital analysis teams have yet to produce a peer-reviewed, widely accepted detection of significant non-gravitational acceleration. The upper limits on such acceleration remain frustratingly low, so insignificant that they challenge our expectations, especially given the visible evidence of activity. This persistent discrepancy positions Atlas in a unique space, one where observable signs of activity coexist with an absence of detectable dynamical effects. In fact, we are witnessing a pair of anomalies that seem to bracket the expected behaviors of such objects. Oumuamua, for example, displayed an excess of non-gravitational acceleration without any visible cause, no outgassing, no jets, making it a profound mystery. Conversely, Atlas appears to demonstrate a visible cause, outgassing and plume formation, yet shows no corresponding dynamical response. Both cases challenge prevailing models of small-body physics when they venture close to our Sun, and both have attracted widespread scientific attention for this reason. These twin anomalies suggest that our current understanding of how interstellar objects behave under solar influence may be incomplete or perhaps fundamentally flawed in some cases. The broader implications extend beyond mere academic curiosity. If we are unable to predict how such visitors will respond to the Sun's heating, whether through outgassing, radiation, or other forces, our capacity to study and interpret these objects diminishes. How can we effectively differentiate between natural fluctuations inherent to comet physics and influences that might be artificial in origin? This question becomes increasingly urgent as upcoming advancements in survey telescopes promise to uncover more anomalous objects, compelling us to sharpen our analytical tools. Before drawing conclusions, however, we must scrutinize the chemical signatures that objects like 3I Atlas leave across the spectrum, signatures that harbor clues some researchers find profoundly perplexing. Let us focus now on Part 4, which centers on the presence of nickel in the comet's coma. The world's largest telescope, situated in the arid expanses of Chile's Atacama Desert, has dedicated decades to unraveling the chemical makeup of distant celestial bodies by dissecting starlight through spectroscopy. When its advanced spectrograph was directed toward 3I Atlas, it detected something that defied conventional understanding. A chemical fingerprint so unusual that it demands rigorous explanation. Specifically, the spectrum revealed distinct emission lines associated with neutral nickel atoms, yet conspicuously lacked corresponding lines for iron. This discrepancy constitutes a cosmic chemistry puzzle, prompting us to question what processes could produce such a pattern. In the language of astronomical spectroscopy, these features are identified as nickel-1 and iron-1 lines. These lines correspond to neutral atoms of these metals that have been excited by solar radiation, causing them to emit light at characteristic wavelengths. Typically, in most comets observed over the course of history, nickel and iron tend to appear together at roughly similar levels, a logical outcome considering their shared origins. Both metals are forged in the intense furnaces of stars, then incorporated into planetary materials as complementary elements. They usually travel together through space, embedded within the same mineral matrices. The numbers paint an even clearer picture. The spectroscopic data displayed unmistakable nickel emission lines, bright and prominent, yet the expected iron lines remained beneath the detection threshold. This creates an unusual chemical profile that stands out sharply against the backdrop of known cometary compositions and demands explanation. Alongside the nickel, astronomers also detected cyanide molecules, CN, whose production rates increased steadily as 3I Atlas drew closer to the Sun. This observed increase aligns well with standard comet physics, which predicts that sublimation of ices like water and cyanide should intensify under solar heating. However, the presence of nickel without a corresponding iron signature defies this general pattern. To account for such anomalies, planetary scientists worldwide are actively exploring several natural explanations. One possibility is space weathering. Over time, the surface of the comet could be selectively liberating nickel-bearing compounds, such as nickel tetracarbonyl, from the nucleus. Solar ultraviolet radiation would then photodissociate these molecules, releasing nickel atoms that fluoresce at specific emission lines detectable by our instruments. Another avenue involves differences in volatility, how readily different materials vaporize, potentially explaining why nickel appears to sublime before iron. Variations in grain size, surface composition, and thermal processing during the comet's long interstellar journey could influence the sublimation sequence, leading to a chemical puzzle that remains unresolved. The surface layers might be enriched or depleted in certain elements, or thermal metamorphism might have altered the composition in ways that produce this unusual signature. Adding intrigue to this mystery, some commentators have speculated that the nickel-only signature might be a trace of artificial engineering. In particular, they suggest that what we are observing could mirror erosion signatures of nickel-based superalloys, materials specifically designed to withstand extreme temperatures, used in high-performance engineering applications like jet engines and spacecraft propulsion systems. These superalloys are known to shed nickel-rich particulates under operational stress, and if such materials had been used in some form of artificial technology, their erosion could produce the observed spectral signature. This line of reasoning points toward a provocative possibility, that the nickel signature might not be purely natural. Instead, it could represent an engineered signature, perhaps remnants of advanced materials or even purposeful modifications, shedding light on potential artificial influences. While such ideas are still in speculative territory, they underscore the importance of meticulous spectral analysis and open-minded investigation when confronting anomalies that challenge our current understanding. This perspective shifts our understanding from a simple chemistry puzzle into a potential signature of advanced technology, though it remains within the realm of hypothesis rather than confirmed science. The James Webb Space Telescope has introduced yet another dimension to this ongoing chemical enigma, uncovering that 3I Atlas possesses one of the most extraordinary and unusual compositions ever documented in a comet. Its coma, the cloud of gas and dust enveloping the nucleus, exhibits an astonishingly high ratio of carbon dioxide to water, a proportion that ranks among the highest ever observed in any comet studied so far. Meanwhile, the levels of water and carbon monoxide remain comparatively subdued, hinting at formation conditions that may have occurred near a carbon dioxide ice line in its parent stellar system, or perhaps reflecting a thermal history markedly different from that of most objects we have encountered in our own solar neighborhood. This chemical peculiarity could, in fact, offer a natural explanation for the way this object behaves dynamically, specifically the absence of the non-gravitational acceleration typically caused by outgassing forces. Since carbon dioxide sublimates more symmetrically than water ice, it tends to create evenly distributed jets of gas across the surface, rather than focused streams from specific regions. If 3I Atlas's outgassing is predominantly driven by carbon dioxide rather than water, then its activity might produce thrusts that are evenly distributed in all directions, what scientists call isotropic thrust vectors. Multiple sources of CO2 emissions scattered across its surface could generate a complex interplay of forces that largely cancel each other out, resulting in minimal net acceleration despite vigorous overall activity. This convergence of chemical composition and physical behavior uncovers an intriguing link between chemistry and dynamics. The same unusual chemical makeup that accounts for the puzzling nickel signature in its spectrum might also explain why the object appears to resist the rocket effect, forces that usually influence the movement of active comets, without requiring artificial intervention. Instead, natural processes such as the dominance of symmetric outgassing from CO2 could be responsible for both phenomena simultaneously. Yet despite these plausible natural explanations, many questions remain unanswered. Why would an interstellar object possess such an unusual chemistry when compared to typical solar system comets? Did it form in an environment vastly different from our local stellar neighborhood? Could its journey of perhaps millions of years between stars have altered its surface composition through cosmic ray bombardment or other forms of space weathering? These questions emphasize just how much we still do not understand about the formation and evolution of planetary materials in other stellar systems. The chemical evidence confronts us with the possibility that our models of comet composition, developed over decades through studying objects born in our own solar system, may not be universally applicable. 3I Atlas might be revealing what comets from other star systems look like when they form around different types of stars, under distinct chemical environments and in thermal conditions unlike anything we have previously observed or anticipated. If chemistry alone cannot sufficiently explain the lack of measurable thrust, perhaps the answer lies in the sheer scale of the object itself. It is possible that we are dealing with an entity so massive that the standard outgassing processes simply cannot produce enough force to alter its trajectory noticeably. This leads us into what can be called the mass argument, an approach rooted in fundamental physics. Sometimes the simplest principles offer the deepest insights. The rocket equation, which governs how spacecraft generate acceleration through propellant expulsion, also applies to comets and other small bodies. It states that the acceleration produced is directly proportional to the gas flow rate and exhaust velocity, and inversely proportional to the mass of the object. In the case of 3I Atlas, if it truly possesses an immense mass, so large that the outgassing of even significant amounts of gas cannot produce observable changes in its orbit, then it could naturally explain the absence of detectable non-gravitational acceleration. This idea hinges on the notion that a sufficiently massive nucleus would have enough inertia to effectively resist the small pushes from outgassing forces, making it appear dynamically stable despite active sublimation processes. Such a scenario suggests that the object's mass might be so substantial that the usual physics of comet behavior no longer applies straightforwardly, opening the door to interpretations that challenge our current understanding of small body dynamics in space. In summary, by considering the fundamental physics involved, it's possible to gain profound insights into the nature of this interstellar visitor, revealing that sometimes the most straightforward explanations, like mass, can offer the key to unraveling even the most complex and puzzling phenomena. The fundamental principle governing rocket propulsion states that thrust equals the rate at which mass is expelled multiplied by the velocity at which it's ejected. When we invert this relationship by measuring the thrust and estimating the outflow velocity, we can, in theory, determine the mass of the object in question. This approach, applied to the interstellar object known as 3I Atlas, has led researchers to startling conclusions that challenge our existing understanding of such visitors from beyond our solar system. On August the 6th of 2025, the James Webb Space Telescope's near-infrared spectroscopic instrument, its highly advanced capability to dissect light, focused on 3I Atlas, providing an unprecedented detailed measurement of its carbon dioxide plume. This instrument's data allowed scientists to accurately calculate the rate at which gas was being produced and the velocity at which it was flowing outward, measurements that are virtually impossible to obtain with ground-based telescopes due to atmospheric interference and the limitations of terrestrial observation. When these gas production rates and outflow velocities are combined with the upper limits on non-gravitational acceleration, obtained through meticulous orbital modeling, the picture that emerges is of an object potentially far more massive than its brightness alone would suggest. One prominent interpretation, championed by notable researchers including Harvard's eminent astrophysicist Abraham Loeb, posits that this object's nucleus could weigh at least 3.3 times 10 to the 10th metric tons. To grasp the scale, this mass is roughly comparable to a small mountain, compressed into a seemingly modest comet nucleus, yet with a mass orders of magnitude higher than anticipated for an object of its size. This concept of an anomalously massive body has begun to permeate scientific literature and conference discussions. Terms that, within current astrophysical paradigms, suggest something that should not exist. According to standard models, typical comets of similar brightness, size, and activity levels should not possess such enormous mass. Should this estimate hold true, it provides a compelling explanation for the missing non-gravitational acceleration. The object's immense mass acts like a form of inertia, capable of absorbing the momentum carried away by the escaping gases without noticeably altering its trajectory. Imagine trying to push a colossal cargo ship with a garden hose. While the thrust is real and present, the ship's massive inertia renders it virtually unresponsive to the forces acting upon it. The expelled gases produce thrust, but the object's considerable mass prevents it from tumbling or drifting as a smaller, less massive comet would. This Newtonian physics-based reasoning elegantly accounts for the observed stability despite active outgassing. However, a crucial challenge remains. Estimating the mass of distant celestial bodies is inherently fraught with uncertainty. Efforts to constrain the true size and reflectivity, or albedo, of 3I Atlas continue unabated. The brightness of its coma, the shroud of gas and dust enveloping it, can be deceptive. A large, dark object may appear similar to a smaller, brighter one, leading to vastly different mass estimates. When the nucleus remains unresolved even through the most powerful telescopes, these differences can amount to orders of magnitude, complicating efforts to pin down its true mass. This persistent uncertainty lies at the heart of why 3I Atlas continues to puzzle researchers worldwide. If the mass estimate is accurate, it compels us to reconsider how such massive, dark objects could form in interstellar space, possibly as dense cores of rock and metal, the remnants of catastrophic cosmic events, or the byproducts of processes vastly different from those in our solar system. The formation mechanisms capable of producing such colossal, obscured nuclei remain elusive and poorly understood within current astrophysical models. Conversely, if the mass is more in line with conventional expectations, more typical for objects of similar brightness, then the original enigma persists. Why does active outgassing, which theoretically should produce a measurable acceleration, seem to have little to no dynamical effect? This discrepancy between observed activity and the lack of corresponding movement remains a profound puzzle, challenging our understanding of the physics governing these cosmic travelers. The compelling nature of the symmetry argument intensifies, pointing toward a scenario where the rotation and surface characteristics of the object collaborate to produce a remarkably balanced outgassing pattern. This finely tuned equilibrium appears to minimize the net thrust exerted on the body, even amid substantial overall activity. Such a phenomenon challenges our current understanding of cometary physics, as it suggests a level of surface and rotational harmony that seems almost unnatural. Either explanation pushes the boundaries of scientific knowledge in profound ways. On one hand, the idea of an anomalously massive object confronts the traditional models of planetesimal formation and the evolutionary processes that shape small bodies in space. Conventional theories posit that objects of such enormous mass should exhibit detectable dynamical effects due to their outgassing activity, yet observations defy this expectation. On the other hand, the possibility of perfectly balanced outgassing patterns, the kind that would neutralize net thrust, challenges the chaotic and unpredictable nature we typically associate with comet surface activity. Comets in our solar system are generally thought to harbor irregular jets and asymmetric outgassing zones that produce measurable thrust and orbital deviations. Both of these scenarios hint at a universe where interstellar visitors might obey rules quite different from those governing the objects we have studied for centuries within our cosmic neighborhood. The implications are profound. If these bodies can operate under different physical regimes, then our assumptions about their formation, structure, and behavior require significant revision. Furthermore, the mass argument raises intriguing questions about detection methods and observational biases. Could it be that we have been systematically missing out on a class of massive, dark objects, simply because they do not brighten significantly as they approach the sun? Unlike typical comets that develop prominent tails and outgassing plumes, perhaps many interstellar objects pass through our observational reach without producing dramatic visible phenomena, slipping by unnoticed in our surveys. This possibility suggests a hidden population of interstellar visitors, massive, inert, or minimally active, that evade detection because they lack the telltale signs we rely on to identify such objects. This concern becomes even more pressing considering the fact that, within a span of just 8 years, humanity has already detected 2 highly unusual interstellar objects, UFO and 3 Atlas, that challenge our understanding of comet physics in opposite directions. UFO exhibited behavior that implied non-standard, perhaps even artificial dynamics, whereas 3 Atlas presents the opposite puzzle. Visible activity without the expected dynamical effects. This pattern raises the question of whether these are mere coincidences or whether they point to systematic gaps in our knowledge of how objects behave when they travel between stars and encounter the sun's influence. The context set by our first interstellar visitor, UFO, adds crucial perspective to this mass mystery because it demonstrated that what initially seems impossible can, with meticulous analysis, become merely improbable, yet still within the realm of natural physics. Let us revisit what lessons UFO taught us starting October 19, 2017, when the Pan-STARRS telescope in Hawaii first detected what appeared to be a faint asteroid. Within days, astronomers recognized that they were witnessing something extraordinary. Humanity's first confirmed interstellar visitor. Named UFO, a Hawaiian word meaning scout or messenger, this object would fundamentally challenge our understanding of how small bodies behave in our solar system. At first glance, UFO appeared to be a lifeless, inert rock. No visible coma, no dust tail, and no signs of outgassing activity that are typically associated with comets as they near the sun. It seemed to tumble through space like a dead fragment, following a hyperbolic path that unmistakably indicated an origin from outside our solar system. Yet despite its seemingly inert appearance, precision orbit determinations revealed an extraordinary phenomenon. UFO was accelerating, exhibiting non-gravitational acceleration incompatible with purely gravitational modeling. The magnitude of this acceleration was approximately Chatir Tochka, deviate times 10 to the negative sixth meters per second, squared at a distance of 1 astronomical unit from the Sun. Its inverse square dependence on the Sun's distance strongly suggested that radiation pressure or outgassing, mechanisms well understood in comet physics, might be responsible. But here's what made this discovery so puzzling. The object showed no visible signs that would account for the force acting upon it. Its smooth, featureless surface and the lack of a detectable coma or tail did not align with the expected outgassing behavior of a typical comet. This discrepancy opened a floodgate of scientific inquiry and debate. Was something about UFO's surface or internal structure preventing the formation of a visible coma? Could it be that the outgassing was occurring in a way that escaped our detection, perhaps as a transparent or highly collimated jet, thus exerting force without revealing itself? Alternatively, was the acceleration caused by radiation pressure on an unusually reflective, perhaps even artificially coated surface? In essence, UFO forced us to re-examine our assumptions. It challenged the notion that visible activity must accompany the dynamical effects of outgassing. The case exemplified the importance of careful analysis in disentang. The detection of acceleration in the case of the interstellar object, famously known as Oumuamua, was profoundly significant from a statistical standpoint. So much so that it was measured at a confidence level of 30 standard deviations. To put this into perspective, such a level of certainty implies that the likelihood of this acceleration being merely the result of a measurement error was virtually zero. Despite this, astronomers found themselves confronting a perplexing conundrum. No visible signs of outgassing or dust emission accompanied this strong force. This absence of detectable material ejected from the object presented what experts diplomatically refer to as an intriguing problem. How could one explain the acceleration of what appeared to be an inert, seemingly passive object, without any observable mechanism? No jets of gas, no dust trails acting as a propellant. Classical physics, grounded in well-established principles of celestial mechanics, dictated that for an object to undergo such orbital acceleration, there must be some form of mass ejection, be it gas or dust, that transfers momentum and thus alters its trajectory. In essence, the physics demanded the presence of a thruster, even if it was microscopic. Yet every telescope and observational instrument that trained its gaze upon Oumuamua failed to detect the expected emissions. No spectroscopic signatures of outgassed molecules, no dust clouds or jets, nothing that could naturally explain the observed dynamical behavior. This disparity sparked a wave of scientific debate and curiosity, leading to the publication of dozens of research papers exploring increasingly unconventional and exotic possibilities. Several hypotheses emerged as scientists attempted to reconcile the anomaly. One suggestion was that perhaps solar radiation pressure alone could account for the acceleration if the object possessed an extraordinarily high area-to-mass ratio, meaning it was extremely lightweight relative to its surface area, making it susceptible to the gentle push of sunlight. Alternatively, some proposed that the object might be venting transparent gas, so elusive that it escaped detection by standard spectroscopic methods, that nonetheless provided enough thrust to influence its orbit. Others speculated that its highly elongated, unusual shape could have amplified thermal re-radiation effects, causing it to respond differently to solar heating than typical bodies, thereby generating additional force. Each of these proposed explanations, however, required bold assumptions that stretched the boundaries of conventional comet physics to the breaking point. Most notably, some researchers floated the provocative idea that perhaps Oumuamua was not a natural object at all. Its peculiar trajectory, extreme aspect ratio, and the mysterious acceleration led to widespread speculation that it might be of artificial origin, potentially a piece of alien technology, an artifice designed by an extraterrestrial civilization. This idea captured the imagination of the public and ignited intense debate within the scientific community, dividing opinions and fueling a flurry of hypotheses. Headlines circulated with sensational claims ranging from alien probes to solar sails, though peer-reviewed scientific papers approached such ideas with cautious skepticism, emphasizing the need for rigorous evidence. The significance of Oumuamua's case extended well beyond its own peculiarities. It became a symbol of how anomalous observations can catalyze scientific progress. The unusual behavior, too much non-gravitational acceleration without any visible outgassing, challenged existing models and prompted researchers to refine their understanding of small body physics, radiation effects, and thermal processes. Ultimately, what began as an inexplicable acceleration transformed into a driving force for advancements in observational techniques, theoretical modeling, and the broader search for interstellar visitors. The puzzle of Oumuamua, with its perplexing combination of unexplained forces and absent signals, served as a catalyst for re-evaluating the assumptions underlying celestial dynamics and opened new avenues for exploring the diverse and potentially surprising nature of objects journeying between the stars. Most notably, Oumuamua set an essential precedent for how we approach anomalous interstellar objects with rigorous scientific discipline. In the realm of extraordinary phenomena, the guiding principle is clear. Exceptional claims demand exceptional evidence, yet this is only part of the equation. True scientific inquiry also requires meticulous attention to detail, a willingness to entertain possibilities that challenge established conventions, and a steadfast commitment to reproducibility and verification. The experience of studying Oumuamua compelled astronomers to broaden their theoretical frameworks, forcing a careful expansion of models while adhering to strict standards of proof. This rigorous approach, refined over 8 years of detailed analysis, from precise astrometric data reduction to thermal modeling, and even to exploring the more exotic hypotheses, has laid a solid methodological foundation. It now serves as the cornerstone for understanding our newest interstellar visitor, 3I Atlas, with all its contrasting behaviors and surprising anomalies. Yet amid these lessons from the outliers, there's a valuable insight that often goes underappreciated. Perhaps the most profound knowledge arises not from objects that defy expectations, but from those that behave exactly as predicted. This theme forms the core of Part 7, titled Lessons from 2 Borisov. On August 30th in the year 2019, amateur astronomer Gennady Borisov, working from Crimea, first observed what he initially believed to be a comet wandering in the constellation Lynx. In the weeks that followed, meticulous orbital calculations confirmed something truly extraordinary. 2I Borisov was indeed an interstellar object, the second confirmed visitor from beyond our solar system. Unlike Oumuamua, which had perplexed scientists with its unusual motions and properties, Borisov's behavior aligned perfectly with our existing understanding of comet physics. In essence, Borisov arrived as a natural control experiment, a cosmic demonstration that interstellar origin does not necessarily equate to anomaly. Its observed dynamics offered textbook validation that objects from other star systems can conform entirely to the physical laws governing solar system comets. As Borisov drew nearer to the Sun, familiar signs of activity emerged. Water and other volatile compounds sublimated from its nucleus, creating the characteristic glowing coma and elongated tail visible through telescopes around the world. Spectroscopic investigations revealed a chemical signature consistent with what we observe in our own planetary neighborhood: water vapor, carbon monoxide, and other molecules that define typical comets. The physical appearance, composition, and activity pattern of Borisov fell within expected ranges for a pristine first-approach comet. an object experiencing its initial encounter with stellar heating. Most crucially for our current exploration, Borisov exhibited non-gravitational acceleration that matched our theoretical predictions with reassuring precision. Measurements indicated a tiny but measurable acceleration on the order of roughly 3.8 times 10 to the negative 7th meters per second squared, observed at a distance of 2 astronomical units from the Sun. This value was completely consistent with the gas production rates and outflow velocities derived from spectroscopic and thermal data. What makes this so significant is that the rocket effect, the small but persistent push resulting from escaping gases, operated exactly as the laws of physics suggest it should. When astronomers calculated the momentum transfer from sublimating gases and compared that to the observed orbital perturbations, the numbers harmonized beautifully. This confluence of observation and theory provided a crucial validation. The fundamental physics that govern small body dynamics in our solar system are robust, unchanging, and universally applicable, even on interstellar scales. Borisov thus reaffirmed that natural objects from other star systems obey the same physical laws, reinforcing our confidence in current models of comet behavior and orbital mechanics. In sum, Borisov's arrival served as a natural benchmark, an unambiguous case where interstellar origin coincided with fully expected physics, allowing scientists to calibrate their models and confirm their understanding. It demonstrated convincingly that not all interstellar visitors are anomalies. Many can fit neatly within the framework of established natural laws, providing a baseline against which to measure the more mysterious objects that challenge our understanding. Regardless of whether these objects originated within the confines of our solar system, or have journeyed across the vast reaches of interstellar space over millions of years, the significance of their study extends far beyond simply confirming their origins. The case of Borisov, for instance, demonstrated convincingly that an interstellar origin does not automatically translate into bizarre or mysterious physics. Instead, objects from distant stellar systems can adhere to the same fundamental natural laws, undergo identical chemical processes, and respond to solar heating in ways that are entirely predictable and consistent with laboratory-tested physics. This realization underscores the importance of the behavior we observe, such as sublimation, outgassing, and tail formation, as being rooted in well-understood natural phenomena. This expected normal behavior makes the anomalies seen in objects like Oumuamua and 3I Atlas all the more remarkable by stark contrast. These objects exhibit characteristics that deviate from the predictable patterns established by objects like Borisov, prompting us to question what processes might be at play. To understand the broader implications, consider what Borisov's behavior tells us about the nature of interstellar objects. Having spent roughly 1 million years traveling through the dark void between stars after being ejected from its original system, Borisov nonetheless activated in a manner identical to any comet passing perihelion within our own solar system. Its ice remained ice, the dust remained dust, and the physics of sublimation followed the laws we've confirmed through decades of laboratory experiments. This continuity suggests that interstellar space acts as a preservative environment. Objects retain their original chemistry and structural integrity over immense distances and timescales, rather than transforming into entirely new forms. This preservation principle carries profound implications for fields like astrobiology and comparative planetology. If objects like Borisov carry their primordial compositions intact across light years of interstellar space, then each one becomes a natural messenger, offering us direct samples from other stellar systems. Every spectroscopic measurement, every chemical analysis we perform on these visitors provides invaluable insights into the conditions, materials, and processes that operate in environments light years away. information that would otherwise be nearly impossible to access. Looking back billions of years to the epoch when these objects first formed, the statistical context becomes especially important. Our current sample of confirmed interstellar visitors, 3 objects, spans a spectrum of behaviors. Borisov behaved in a way that was entirely consistent with traditional comet expectations, showcasing predictable outgassing and tail development. Conversely, Oumuamua exhibited moderate anomalies such as unexpected acceleration without visible outgassing, while 3I Atlas presents a more puzzling case, with visible activity but no detectable non-gravitational forces. This small but diverse sample suggests a crucial insight. While many interstellar objects might behave predictably, a significant fraction defy our current understanding, exhibiting characteristics that challenge or extend our theoretical frameworks. Borisov's exemplary alignment with known physics also serves to reinforce the reliability and accuracy of our observational techniques and analytical methods. When our instruments and models produce results consistent with laboratory physics, it affirms that we are correctly interpreting the data and understanding the natural processes at work. This confidence is crucial because it underpins our ability to study more unusual objects like 3I Atlas. If the methods are validated in the context of normal, predictable cases, then discrepancies observed in anomalous cases are more likely to reflect genuine physical differences rather than errors or biases in our measurement techniques. This lesson extends into the realm of future discoveries. The upcoming Vera Rubin Observatory promises to revolutionize our detection capabilities by increasing the rate of interstellar object discoveries by orders of magnitude, potentially revealing dozens or even hundreds of such objects in the coming years. Borisov's behavior suggests that many of these future objects will prove mundane in terms of fundamental physics. They will serve as valuable representatives for comparative planetology, helping us refine our models and understanding of small bodies, but they are unlikely to challenge our core physical principles. Instead, these normal objects will establish a statistical baseline, a reference framework against which we can more confidently identify truly anomalous objects, those that deviate in ways that might hint at new physics, artificial origins, or previously unknown natural processes. In essence, Borisov's case provides a foundation of expectation, a reassurance that most interstellar visitors will behave within the bounds of known physics, thus allowing us to spot the outliers, like Oumuamua and 3 Atlas, that truly push the boundaries of our understanding. These outliers, while rare, become the key to unlocking new scientific frontiers and possibly even discovering evidence of extraterrestrial technology or phenomena. Even within our own solar system, where centuries of detailed study have deepened our understanding of comet behavior, the intricate relationship between a comet's activity, its outgassing, and its resulting movement through space remains surprisingly complex. It is tempting to assume that larger, more active comets would invariably display proportionally greater non-gravitational effects due to their vigorous emissions. Yet reality often defies this straightforward expectation. Even sizable comets with dramatic jets of sublimated gases can show significant deviations from purely gravitational trajectories, reminding us that an object's mass alone does not dictate how it responds to its own ejected material. Let's consider some benchmark examples to illustrate this point more concretely. The comet 67P Churyumov-Gerasimenko, which measures just about 4 kilometers across at its widest extent, became famously well studied during the European Space Agency's Rosetta mission. Over a remarkable 12-year period, Rosetta functioned as a dedicated escort, orbiting, analyzing, and photographing this modest-sized comet with unprecedented detail. Every prediction rooted in physics held true. The forces generated by outgassing created measurable pushes, non-gravitational accelerations, that altered its orbit in ways consistent with theoretical models. Instruments positioned mere kilometers from the nucleus detected jets of sublimating material erupting from specific surface features, while mass spectrometers decoded the chemical makeup of the escaping gases. Dust detectors recorded impacts from tiny particles lifted off the surface, providing direct evidence of active surface processes. When mission planners combined all this in situ data, gas production rates, jet velocities, and surface chemistry, they could accurately compute the total thrust produced by outgassing. Astonishingly, these calculations precisely matched the orbital deviations observed in real time, confirming on a microscopic level the physics of cometary motion as understood in theory. This validation was crucial because it eliminated any ambiguity about the physical mechanism, outgassing being the primary driver, behind non-gravitational effects. Such high-resolution direct measurements established a foundational understanding. When gases sublime from a comet's surface, they generate forces that influence the body's trajectory. These forces depend predictably on three main factors: the rate at which gases are produced, their exhaust velocities, and the mass of the nucleus itself. The relationship is straightforward and well-tested. More outgassing, faster jets, or a lighter nucleus results in a more noticeable acceleration. Scaling this understanding up, one might expect that larger objects with greater outgassing would produce proportionally larger effects. However, the picture becomes more complicated as size increases. Larger nuclei tend to have more inertia, which dampens the acceleration effects of their emissions. This leads us to the case of Comet Hale-Bopp, one of the most spectacular comets observed in recent history. During its 1997 apparition, Hale-Bopp's nucleus was estimated at about 60 kilometers in diameter, roughly 15 times larger than 67P. Despite its immense size, Hale-Bopp still exhibited measurable non-gravitational acceleration as it approached the Sun, demonstrating that even massive comets cannot fully resist the rocket effect of their own outgassing. This lesson is directly relevant to the ongoing mystery of 3I Atlas. While mass confers a certain level of inertia, resisting changes in trajectory, it does not completely negate the influence of outgassing forces. According to the most recent, albeit highly speculative estimates, 3I Atlas might possess a nucleus with a mass on the order of 10 billion metric tons. Even at this enormous scale, if the jets of gas are sufficiently powerful and focused in particular directions, they should produce some measurable acceleration. This is especially true if the outgassing is asymmetric, that is, concentrated in jets pointing preferentially in certain directions, since such directional bias would produce a net push on the object's trajectory. This brings us to a critical aspect of comet physics: the importance of symmetry and vent geometry. The precise configuration of active regions, where jets emerge, their orientation, and their combined effects, determines whether the net acceleration is significant or effectively cancelled out. If the active vents are arranged symmetrically around the nucleus, the forces can balance each other, resulting in little to no overall change in the comet's trajectory despite vigorous activity. Conversely, even a modest asymmetry, just one stronger jet pointing in a particular direction, can produce a measurable push, altering the orbit in predictable ways. Understanding this balance is essential because it explains why some comets exhibit strong outgassing signatures yet show minimal orbital deviations, while others display clear non-gravitational effects even with comparatively modest activity. The geometry, distribution, and physical configuration of vents and jets act as the control knobs for how a comet's emitted gases influence its movement in space. For 3I Atlas, whose behavior continues to puzzle scientists, the question of vent symmetry and geometry may hold the key to understanding why observed activity does not correlate straightforwardly with predicted dynamical effects. Detailed computer simulations of comet outgassing, rigorously validated through direct spacecraft observations, reveal that the way active regions are distributed across a comet's surface plays a crucial role in determining whether the jets of sublimating gases reinforce each other or cancel out. Imagine a nucleus whose vents, those areas where gases escape, are scattered randomly in various directions. Such an arrangement could produce an impressive visual spectacle with dramatic plumes and jets, yet result in a net thrust so minimal that the comet's overall motion remains virtually unaffected. This phenomenon occurs because the individual outgassing forces, when randomly oriented, tend to balance each other out, producing a subtle or even negligible push on the nucleus. Astronomers incorporate these complex effects into their orbital models by defining what are known as the A1, A2, and A3 parameters, mathematical factors that describe how the non-gravitational forces acting on the object vary, depending on its distance from the Sun and its position along the orbital path. In the early stages of an object's journey through the inner solar system, these parameters often carry significant uncertainties. This is primarily because insufficient time has passed to accumulate enough tiny positional shifts, those minute deviations from purely gravitational motion, that would allow scientists to reliably discern systematic non-gravitational influences. The importance of the object's time within observation cannot be overstated. Measuring such subtle accelerations demands patience, requiring astrometric data collection over months or even years. When observations are limited, especially for objects discovered late in their approach to the Sun, many interstellar visitors fall into this category. The observational baseline becomes short. This constraint hampers the precision of dynamical analyses, making it challenging to detect or rule out small accelerations. What might seem like no measurable acceleration could simply be an artifact of insufficient measurement time, rather than evidence of a genuinely inert object. Nonetheless, when we consider the broader context of comet behavior, the case of 3I Atlas remains strikingly anomalous. Most active comets within our solar system display detectable non-gravitational effects within just weeks or months after their activity begins, driven by the sublimation of volatile materials. The fact that 3I Atlas shows ongoing signs of outgassing yet exhibits no such measurable dynamical push is statistically unusual. This persistent absence of detectable acceleration, despite clear evidence of active outgassing, continues to set this object apart from both interstellar and native solar system populations. Decades of cometary research have established benchmarks, predictable patterns of activity and motion that 3I Atlas appears to defy. Whether the reason is an extraordinary mass that absorbs outgassing momentum without noticeable movement, an almost perfect symmetry in its outgassing jets that cancels out net forces, or some other unrecognized physical mechanism, this object challenges our current ability to predict how bodies behave when subjected to stellar heating. Such anomalies often signal the potential for groundbreaking scientific discoveries. They are moments when nature presents phenomena that have yet to be codified into our textbooks, offering clues that could expand or even overturn existing theories. But a provocative question arises. What if the explanation for this unusual behavior does not involve exotic physics or unconventional formation histories? Instead, could it be the result of deliberate conscious intervention, an artificial stabilization of the object's trajectory? This speculation warrants serious, careful examination, especially if only to understand why some researchers consider it a plausible hypothesis worthy of scientific discussion. In the realm of peer-reviewed science, extraordinary hypotheses are subjected to rigorous scrutiny. They are evaluated carefully for the quality and consistency of the evidence supporting them. The artificial control hypothesis for 3I Atlas falls into this rarefied category. While it is speculative enough to raise eyebrows and challenge conventional wisdom, it is also grounded in a sufficient number of anomalous observations that dismissing it outright might be considered an oversight, an intellectual negligence, given the current state of evidence. Let's explore this scenario with the meticulous care and methodological rigor that science necessitates, all the while maintaining a clear boundary between well-founded facts and mere speculation. At the heart of this inquiry lies a straightforward yet profound engineering question. If the goal were to send a probe across interstellar distances while minimizing any detectable signs of artificial propulsion, how would one go about designing such a craft? The answer to this question draws upon principles of advanced spacecraft engineering, emphasizing subtlety, stability, and stealth. One conceivable approach involves the use of active stabilization systems, tiny thrusters or reaction control mechanisms that can counteract the small, unpredictable forces acting upon the probe. These forces might originate from natural outgassing, temperature-induced sublimation, or even residual momentum from previous maneuvers. To remain undetected, the craft would need to compensate for these influences with precision, employing micro-thrusters that deliver gentle, carefully calibrated pushes in opposition to the minor outgassing or other sources of drift. Cold gas micro-thrusters are an excellent example. These devices can produce extremely fine control over the craft's attitude and trajectory. By providing minute amounts of propulsion precisely when needed, they could cancel out any unintended accelerations caused by natural processes. Symmetrically arranged reaction control systems, jets positioned evenly around the craft, might help balance asymmetric gas emissions, ensuring that the net thrust remains effectively zero. Complementing these, momentum wheels or reaction wheels could help maintain orientation without the need for continuous thruster firing, further reducing detectable signals. Moreover, the surface properties of the probe could be engineered with smart materials, substances capable of adjusting their thermal and emission characteristics dynamically. Such materials might alter surface heating patterns or gas emission directions in real time, actively managing outgassing behavior to produce minimal net force and thereby evade detection. It's important to recognize that none of these techniques belong to the realm of science fiction. Human-made spacecraft have employed similar systems for decades. For instance, the International Space Station uses reaction control thrusters to compensate for atmospheric drag and maintain its station-keeping position. Deep space probes, such as those traveling far beyond the influence of Earth's gravity, carry sophisticated attitude control systems to ensure precise pointing, despite the persistent pressure of solar radiation and thermal effects. The engineering principles behind these systems are well established and proven. The real question then centers on scale, complexity, and intent. How large and sophisticated would such a stealthy system need to be? And what motivation would drive the creation of such an object? Consider the intriguing spectroscopic signature, nickel without iron, that has puzzled scientists analyzing the emissions from the interstellar visitor known as 3I Atlas. In the realm of advanced engineering, nickel-based superalloys are the material of choice for components exposed to extreme temperatures. These superalloys are the gold standard because they can withstand the intense heat generated in jet engines, rocket nozzles, and spacecraft propulsion systems without vaporizing. Under operational stress, such materials naturally shed tiny nickel-rich particulates, an erosion signature that in principle could be mistaken for debris from an advanced propulsion system. Could we be witnessing an erosion pattern indicative of high-temperature engineering, perhaps even of artificial origin? The observations of nickel emissions, as documented in studies using the Very Large Telescope, have proposed natural explanations involving space weathering and photodissociation chemistry, processes that alter material surfaces over time in the harsh environment of space. However, some scientists and commentators have pointed out the intriguing similarity to wear patterns seen in high-temperature engine components, raising the possibility that what we interpret as natural surface erosion might in fact be a technological signature. This notion remains speculative, a hypothesis not yet supported by conclusive evidence. Abraham Loeb, a prominent astrophysicist, has contributed to this debate by analyzing the inferred mass of the object. If, as some estimates suggest, 3 Atlas weighs around 3.3 times 10 to the 10th metric tons, roughly comparable to a small mountain, then we are dealing with something on a scale that vastly exceeds most human engineering projects. Such mass could be interpreted in 2 ways, either as a natural density concentration, perhaps a dense metallic core, or as the signature of a constructed object designed for long-term interstellar travel. The ambiguity arises because the mass estimates are based on photometric data, which can be influenced by surface reflectivity, porosity, and other factors. Until better observational constraints are available, both interpretations remain plausible. Finally, the trajectory characteristics of 3 Atlas have also garnered attention from both scientists and theorists. Some have speculated that the path it follows might show signs of deliberate navigation, suggesting purposeful course corrections, while others see it as a natural consequence of gravitational interactions and initial ejection conditions. This ongoing debate underscores the importance of approaching such phenomena with both scientific skepticism and openness to new possibilities. Recognizing that our current understanding is still evolving, some investigations propose that the trajectory of this object hints at deliberate navigation, suggesting it may be maintaining precise orientations relative to the ecliptic plane, the imaginary line that marks Earth's orbital path around the Sun. These objects appear to be approaching from directions that could optimize their capacity to harness solar energy, possibly aligning themselves to gather maximum power during their passage through our solar system. Moreover, their trajectories seem to follow patterns that would allow for extended observation windows, potentially enabling detailed scrutiny of our planetary environment or the Sun itself. Such behavior could be interpreted as following natural orbital mechanics, especially considering scenarios where objects ejected from distant stellar systems settle into stable or semi-stable orbits shaped by gravitational interactions. However, these patterns could also be indicative of intentional course adjustments, subtle, purposeful corrections designed to enhance scientific or reconnaissance objectives, suggesting an advanced level of control and planning. Beyond these interpretations, more provocative theories have begun to circulate, especially in preprint archives and specialized online forums. Some researchers and enthusiasts have speculated that this object might exemplify what science fiction terms dark forest technology, autonomous probes crafted to study other civilizations while employing strategies to remain undetectable. These ideas extend well beyond the boundaries of mainstream scientific consensus, reflecting the profound cultural and imaginative influence that truly anomalous interstellar visitors have on the public mind. They serve as fertile ground for speculative thinking about the existence of unseen technology or covert observational platforms lurking in the depths of space. The hypothesis that such an object might be artificially controlled demands a high standard of evidence because it advances extraordinary claims concerning the nature of extraterrestrial intelligence. To substantiate an artificial origin, scientists would need multiple converging lines of proof. Clear, systematic deviations from known natural physics that cannot be explained through current models. Technological signatures, such as unusual materials, emission patterns, or behaviors, that cannot be accounted for by known geological or chemical processes, and behaviors that strongly suggest purposeful control rather than randomness or natural drift. As of now, the object in question, often referred to by its designation, exhibits several intriguing anomalies, yet it does not fully meet these rigorous criteria. The absence of detectable non-gravitational acceleration, for instance, could well be the result of natural processes that we do not yet understand. Perhaps unique formation conditions or internal structures that mitigate such effects. Its unusual chemical composition might stem from formation environments quite different from those in our solar system, involving volatile substances or mineral assemblages unfamiliar to terrestrial science. Additionally, the apparent mass concentration could be a natural density variation within its structure, rather than evidence of artificial construction or assemblage. Nonetheless, considering these possibilities plays an essential role in expanding our scientific perspective. Instead of limiting ourselves solely to traditional comet or asteroid physics, which might overlook subtle signs of artificial origin, exploring alternative hypotheses encourages a more comprehensive inquiry. Historically, astronomy has seen numerous instances where seemingly impossible observations led to revolutionary insights, revealing new natural phenomena or challenging fundamental assumptions about the universe. Recognizing this, scientists emphasize the importance of maintaining a healthy skepticism while avoiding premature conclusions, a balance that guards against both complacency and unwarranted suspicion. Ultimately, while the available data on this object, often called by its designation, presents enough anomalies to justify broader theoretical exploration, it falls short of the conclusive evidence needed to confirm any exotic or artificial explanation. The scientific process requires a high threshold of proof, especially for claims that challenge established paradigms. As such, careful, high-quality observations remain crucial. Only through rigorous analysis, repeatability, and the accumulation of converging evidence can we move closer to understanding whether this interstellar visitor is a natural object with unusual properties or a potential sign of something more extraordinary, perhaps even intelligence, lurking at the edges of our comprehension. Before rushing to any conclusions about the possibility of artificial origins, it is essential that we carefully scrutinize what our most advanced scientific instruments are truly revealing about this object's stability, chemical makeup, and behavioral patterns. To do this, we rely on detailed spectroscopic and imaging analyses that can unveil the intricate details of its physical state and composition. Turning now to the spectral data obtained from the James Webb Space Telescope's near-infrared spectrograph, which doesn't merely gather light but dissects it with extraordinary precision. This instrument acts like a cosmic scalpel, revealing the molecular fingerprints that encode stories of chemical processes occurring over billions of years across the universe. During its observation run on August 6, 2025, JWST focused its gaze on the interstellar visitor known as 3I Atlas. The resulting spectrum painted a portrait of an object unlike any comet previously examined in such detail. The most prominent feature in this spectrum manifests strongly in the near-infrared wavelengths, where molecules of carbon dioxide absorb specific photons and then re-emit them, creating characteristic signatures that serve as unmistakable molecular fingerprints. Remarkably, 3I Atlas displays one of the highest ratios of carbon dioxide to water vapor ever measured in any comet, whether within our solar system or beyond. In the vast majority of comets we are familiar with, water ice dominates as the primary volatile component, reflecting their formation environments in regions where water condenses readily into ice. This results in the familiar ice-rock mixtures that characterize many periodic comets orbiting our Sun. However, the chemical profile of 3I Atlas suggests a different story. It appears primarily powered by the sublimation of carbon dioxide, with water vapor and carbon monoxide playing secondary roles in its activity patterns. This chemical dominance immediately challenges our existing understanding of comet formation. It implies that the object originated in an environment where carbon dioxide was the dominant volatile, possibly near a carbon dioxide ice line around a star of a different type than our Sun, or within a protoplanetary disk characterized by unusual chemical gradients. Such conditions are uncommon in the formation environments of most solar system objects, prompting us to reconsider how and where interstellar comets might form. The implications extend further when considering outgassing symmetry. In typical comets, water ice tends to concentrate in specific regions of the nucleus, often associated with geological features or areas that are preferentially heated, leading to directed jets of material that can be observed with spacecraft. These jets create anisotropic outgassing, which often results in measurable non-gravitational forces acting on the comet, nudging its trajectory over time. By contrast, carbon dioxide sublimates more evenly across the surface, producing what physicists call isotropic outgassing patterns. If 3I Atlas is indeed dominated by carbon dioxide, its emissions are likely to be more evenly distributed, which could naturally produce a balanced thrust profile. Such a profile would minimize or even negate net acceleration effects, despite the comet exhibiting substantial overall activity. Supporting this idea, the Hubble Space Telescope has chronicled the visual evolution of this unusual object across multiple wavelengths and observation epochs. The July 21st image, for example, revealed a distinct plume of gas stretching directly toward the Sun, emanating from the nucleus. This confirmed ongoing active gas emission directed toward our star, rather than being randomly distributed in all directions. Intriguingly, the same observations detected extremely faint features that resemble an anti-tail, a material structure pointing sunward rather than away from it. Such a tail defies simple interpretation under traditional cometary physics, but falls within the natural spectrum of phenomena observed in solar system comets when viewed from specific geometric perspectives. These anti-tail features could be explained by the alignment of the observer, the comet's motion, and the distribution of ejected material, all consistent with natural processes rather than artificial manipulation. By the end of August, detailed observations from the Gemini South Observatory revealed a significant transition in the comet-like object's tail development. What had once appeared as an unusual anti-tail, material that seemed to point sunward, gradually evolved into a more typical cometary tail, with particles clearly streaming away from the Sun under the influence of radiation pressure and solar wind interactions. This progression from atypical anti-tail features to conventional tail structures offers valuable insights into the physical and dynamic properties of the object. Specifically, it constrains our understanding of its rotation period, surface characteristics, and the intricate processes governing how particles of varying sizes respond to solar forces over time. Simultaneously, the most powerful telescopes continued their spectroscopic monitoring of the object, capturing the evolving chemical activity with remarkable detail. The data showed that the production rates of nickel and cyanide molecules increased steadily as the object approached perihelion, the closest point in its orbit to the Sun, matching precisely the behavior anticipated by models of increasing solar heating. Such a correlation reinforces the idea that solar energy is driving sublimation and outgassing processes. Intriguingly, despite this activity, the spectroscopic observations consistently failed to detect any significant amount of iron. It remained below the thresholds of detection throughout the entire period. This persistent absence of iron, contrasted with the rising nickel emissions, has continued to puzzle scientists, prompting ongoing investigations into the natural mechanisms that could produce such an unusual elemental abundance pattern. These meticulous observations set a critical baseline for evaluating claims of the object's stability, despite months of active outgassing, evidenced by the dynamic tail structures and increasing chemical signatures. The measurements of non-gravitational acceleration, derived from precise orbital analyses, have remained at or below the detection thresholds acknowledged in peer-reviewed models. This persistent lack of measurable dynamical effects, even amidst clear signs of ongoing material loss, constitutes one of the core anomalies fueling scientific curiosity. It challenges conventional expectations. Normally, active outgassing should impart a noticeable push, altering the object's trajectory. The fact that it does not suggests an extraordinary stability that defies standard comet physics. To explain this apparent stability, researchers have employed advanced computer simulations exploring various natural scenarios. These models indicate that if the object maintains a symmetric outgassing field, meaning that gases are expelled uniformly in all directions, and if its particle size distribution and rotational state are finely tuned, the net thrust could be minimized. Such a configuration would allow it to exhibit substantial visual activity without producing detectable changes in its orbit. The most perplexing aspect is understanding how the object could sustain such a delicate balance, especially considering that most active comets typically show measurable acceleration within mere weeks of developing significant coma and tails. Adding further complexity, the rotational dynamics of the object likely play a crucial role. Typically, tumbling or irregular rotation exposes different surface regions to the Sun, leading to cyclical variations in outgassing. These variations often produce characteristic acceleration signatures that can be detected and modeled. If, however, the object maintains an unusually stable orientation, perhaps due to surface composition or internal structure, or if its surface properties suppress rotational effects, this could contribute to its apparent dynamical steadiness. Temperature modeling, based on the observed chemical emissions, suggests that the surface conditions are consistent with standard solar heating at its current orbit, with no evidence indicating internal heat sources, exotic thermal regulation mechanisms, or artificial temperature control. The chemistry responds predictably to the increasing solar flux, following well-understood sublimation physics, despite the unusual elemental abundance ratios observed. In sum, these findings reinforce the notion that the comet-like object is behaving in a manner consistent with natural physics, simply operating at the extreme edges of known behavior. Its tail evolution, chemical signatures, and lack of measurable acceleration all align with models of a body undergoing typical sublimation processes driven by solar heating, without revealing signs of artificial intervention or extraordinary internal mechanisms. Yet, despite the wealth of insights we've gained, many profound questions linger about what these observations might mean for the distant future. As 3I Atlas steadily advances toward its perihelion in late October, we find ourselves pondering whether its activity patterns, its visible outgassing, tail evolution, and chemical signatures will continue to exhibit the stability we've observed so far. Will the increasing solar warmth finally breach the mechanisms that have kept its acceleration unnoticeable, revealing forces at work beneath its surface? Or will this enigmatic object persist in defying our expectations, challenging and possibly rewriting our understanding of cometary physics all the way to its closest approach and beyond? The answers to these questions could have a transformative impact on multiple fronts. They might reshape our fundamental theories about interstellar visitors, those rare travelers from beyond our solar neighborhood, and deepen our appreciation for the astonishing diversity of planetary formation processes occurring around stars across the galaxy. Moreover, they could alter our perception of how outgassing activity influences orbital behavior, revealing new dynamics or constraints we hadn't previously considered. But before we venture into these scientific debates, it's crucial to reflect on why these questions matter far beyond mere academic curiosity. Understanding the behavior of such anomalous interstellar objects might hold the key to a revolutionary shift in our search for extraterrestrial intelligence. It could guide us toward new methods, new perspectives, and a broader framework for recognizing signs of life or technology beyond Earth. Part 11. Why this matters to SETI. For the past 70 years, humanity has been quietly listening to the cosmos, deploying ever more advanced radio telescopes in hopes of catching an unmistakable whisper, an electromagnetic signal that would confirm we are not alone in this vast universe. From the pioneering efforts of Project Osmo in the 1960s to the ongoing sophisticated endeavors of the Breakthrough Listen initiative, our focus has largely centered on detecting deliberate messages, intentional signals sent by intelligent civilizations across interstellar distances. These signals, often envisioned as powerful beacons or deliberate broadcasts, serve as cosmic lighthouses announcing the presence of technologically capable neighbors to any capable receiver. This approach, driven by the hope of intercepting intentional communications, has shaped much of our current SETI strategy. It has led to the monitoring of countless stars, scanning broad swaths of the electromagnetic spectrum for signs of alien technology. Beacon signals, laser pulses, or other deliberate transmissions. The iconic Arecibo message of 1974 exemplifies this philosophy. A deliberate, crafted transmission aimed at potential extraterrestrial recipients, showcasing humanity's ability to produce detectable signals. However, recent discoveries like 3I Atlas suggest that this paradigm might be limited or incomplete. These interstellar visitors, which arrive without any apparent attempt at signaling, no deliberate broadcasts or conspicuous beacons, challenge us to consider a broader, more inclusive approach. Instead of waiting for civilizations to advertise their presence, perhaps we should look for signs that are embedded within the objects themselves. Signatures that resist easy explanation and hint at artificial origins. These naturally occurring phenomena, small bodies passing through our solar system, carry within them a wealth of information about their origins, compositions, and histories which no form of electromagnetic jamming or concealment can fully obscure. In essence, the study of anomalous interstellar objects offers us a new avenue for the search for extraterrestrial intelligence, one that does not rely solely on the detection of deliberate signals but also on the analysis of what might be unintended or incidental signatures of technological activity. These objects could be silent messengers revealing their origins and perhaps even their creators through their physical characteristics, chemical compositions, and orbital behaviors. By expanding our perspective in this way, we open fresh possibilities for discovering evidence of other intelligences lurking in the cosmic shadows. If a subset of these celestial objects turn out to be artificial constructs rather than naturally occurring formations, they would serve as compelling evidence that does not rely on deciphering the intentions or communication methods of their creators. This perspective broadens the scope of investigation beyond conventional signals, emphasizing the importance of analyzing physical characteristics and orbital behaviors that might betray artificial origin. Unlike traditional SETI approaches, which focus on continuous monitoring for fleeting electromagnetic signals or deliberate beacons, this alternative framework operates on vastly different timescales and employs distinct methodologies. Instead of actively scanning the skies for transient radio or optical messages, it advocates for a rapid response system, an agile approach that kicks into gear the moment a new interstellar object is discovered and tracked through our observable space. The core of this strategy involves detailed, comprehensive analysis of the object's orbital mechanics, spectroscopic signatures, and photometric behavior. These data points are scrutinized to differentiate natural phenomena from potential artificial signatures, such as unusual trajectories, anomalous chemical compositions, or emission patterns that defy standard natural explanations. Over the past 8 years, this statistical argument for a broadened investigative approach has gained considerable strength. During this relatively short period, we have confirmed the interstellar origins of three objects: Oumuamua, Borisov, and 3I Atlas. Remarkably, two of these, Oumuamua and 3I Atlas, exhibited characteristics that challenge existing natural models of comet and asteroid behavior. Their anomalies suggest that either we have been exceedingly unlucky in our sampling, failing to detect more objects of artificial origin, or that such unusual behaviors are more common than previously assumed. This realization underscores the need for systematic, rather than case-by-case investigation of interstellar visitors to better understand their true nature. The implications of even a small proportion of these interstellar objects being artificial are profound. They could be reconnaissance probes launched by curious extraterrestrial civilizations, designed to gather intelligence about stellar systems without revealing their presence. Alternatively, they might be remnants of discarded infrastructure or defunct machinery from advanced technological species passing through our neighborhood on a routine basis. Current detection methods are primarily optimized for natural objects that follow predictable gravitationally driven orbits. These techniques might overlook or misclassify artificial objects, especially if such objects employ stealth technologies, unconventional propulsion systems, or other methods to evade detection. This expanded SETI philosophy recognizes that highly advanced civilizations could prefer subtlety over overt signals, opting to conduct reconnaissance quietly rather than broadcasting their presence broadly. Such entities might craft probes that generate minimal electromagnetic signatures, follow trajectories indistinguishable from natural bodies, and utilize technologies that mimic the chemical or physical processes we associate with natural objects. For instance, 3I Atlas fits this profile almost perfectly. It is sufficiently anomalous to draw scientific interest, yet ambiguous enough to allow for a natural explanation of each observed characteristic. If these features are the result of deliberate design rather than cosmic coincidence, it would imply a level of technological sophistication that renders traditional SETI assumptions, centered on active broadcasting, both anthropocentric and limited. Integrating the study of interstellar objects with conventional SETI methodologies enables a more holistic and robust search strategy. Instead of relying solely on detecting deliberate signals, this approach considers the possibility that extraterrestrial intelligence might communicate or reveal itself indirectly through the physical properties, trajectories, and chemical signatures of objects passing through our solar system. Such a comprehensive framework enhances our chances of discovering evidence of other technologies, whether intentional or incidental, without depending solely on the assumption that alien civilizations will choose to transmit detectable signals. As humanity continues its quest to decipher the secrets of interstellar visitors, a comprehensive two-pronged approach remains at the forefront. On one side, vigilant radio surveys tirelessly scan the cosmos for deliberate signals that could indicate advanced extraterrestrial civilizations. On the other, rapid response campaigns spring into action whenever a new physical visitor is detected, meticulously investigating its properties for signs of artificial origin. This dual strategy aims to optimize our chances of making a groundbreaking discovery by covering both natural and potentially engineered phenomena, thereby reducing the risk of overlooking subtle hints of intelligence due to preconceived notions or assumptions about alien behaviors. However, orchestrating such an expansive and swift response requires an unprecedented level of coordination among global astronomical surveys, national space agencies, and research institutions. The fleeting windows during which interstellar objects are visible and accessible demand that telescopes be allocated immediately, often within hours of detection, allowing for prompt spectroscopic follow-up and real-time data analysis. These requirements push the boundaries of existing observational infrastructure, demanding systems capable of high-precision measurements and rapid data processing. The upcoming months will thus be pivotal, serving as a testing ground for these innovative strategies. As the interstellar object known as 3I Atlas approaches its closest proximity to the Sun, scientists anticipate that new details about its composition, structural features, and behavioral patterns might emerge, potentially tipping the scales in the ongoing debate over whether it is a natural celestial body or an artifact of alien engineering. Looking ahead, the observational timetable is set for a dramatic climax. The cosmic choreography, governed by precise mathematical laws, is orchestrating what could be the most revealing phase of this celestial dance. On October the 30th, 2025, 3I Atlas will reach perihelion, the point in its orbit nearest to the Sun, at approximately 1.4 astronomical units away. This moment signifies not only the object's closest approach, but also perhaps our last best opportunity to extract definitive answers about its true nature before it recedes into the vast expanse of interstellar space once more. In the realm of observational astronomy, the geometry of the system, specifically the relative positions and angles between Earth, 3I Atlas, and the Sun, dictates the clarity and richness of the data we can gather. As the asteroid swings around perihelion, different regions of its surface will undergo peak solar heating, potentially igniting new outgassing behaviors or exposing variations in its chemical makeup across the nucleus. If indeed artificial systems are responsible for maintaining its trajectory, perhaps through some form of engineered stabilization, then the increasing thermal stress brought on by closer proximity to the Sun might finally exceed their operational limits, resulting in detectable changes in its motion. At the same time, the intensified solar flux will amplify faint spectroscopic signals, making subtle emission lines more observable and allowing scientists to conduct highly precise measurements of isotopic ratios. Such data could become crucial in differentiating natural materials from potential artificial constructs. Trace elements previously below detection thresholds might now produce signals strong enough to shed light on the enigmatic nickel-to-iron abundance pattern that has puzzled researchers since the early days of its observation. The first observational window opens with a unique opportunity. Several Mars orbiters positioned around our neighboring planet will be ideally situated in early October to observe 3I Atlas from angles that are impossible to achieve from Earth-based telescopes. Notably, the Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express are all equipped with vantage points that could reveal new details about the shape of the nucleus, how it rotates, and the activity patterns on its surface. Information that remains hidden from terrestrial observations due to the limitations imposed by our planet's position and atmospheric interference. These spacecraft could provide critical insights during this brief window, enhancing our understanding of the object's physical characteristics and perhaps offering clues about its origin, natural or artificial, by revealing features inaccessible from the ground. The upcoming weeks thus hold the promise of a wealth of new data, as the celestial ballet of objects and forces unfolds in a manner that might finally tip the scales in our ongoing quest to comprehend the true nature of this interstellar visitor. The pursuit of further insights into the enigmatic nature of 3I Atlas hinges critically on the availability of specialized observational data, a pursuit that is inherently constrained by the current priorities and technical feasibility assessments under active discussion at mission control centers across the globe. These considerations, involving spacecraft scheduling and resource allocation, are essential to optimizing the chances of capturing meaningful measurements. Among the most promising avenues for expanding our understanding are opportunistic observations made by deep space missions, even though these spacecraft were not originally designed to study interstellar visitors. For instance, missions such as NASA's Juno orbiting Jupiter, ESA's Jupiter Icy Moons Explorer, JUICE, or NASA's Psyche mission targeting a metallic asteroid could, in theory, leverage their unique vantage points and sophisticated instrumentation to provide unprecedented multi-angle perspectives of 3I Atlas as it approaches perihelion. Achieving such observations would necessitate complex trajectory calculations, precise instrument calibrations, and meticulous planning to align the spacecraft's orbits with the object's position and activity window. Despite the operational challenges, the potential scientific gains, offering detailed insights into the object's physical and compositional characteristics, could justify the considerable effort involved. At the heart of these endeavors lies a fundamental question. What specific data would be sufficient to conclusively resolve whether 3I Atlas is a natural phenomenon or an artificial construct? To tip the balance of evidence decisively, three particular types of measurements stand out as especially critical. The first involves detecting a statistically significant non-gravitational acceleration that correlates directly with the measured outgassing activity. Such a correlation would strongly support a natural explanation rooted in familiar rocket physics, confirming that the object's motion adheres to known principles despite its other peculiar attributes. If, on the other hand, the object exhibits persistent, minimal, or undetectable acceleration, even as its activity appears to intensify, this would bolster the hypothesis that its behavior is maintained by some form of artificial stabilization, defying conventional physics. Achieving the precision necessary for these measurements pushes the boundaries of current astrometric capabilities, demanding meticulous error analysis and the corroboration of findings across multiple independent teams and observational platforms. The second, equally vital measurement involves obtaining resolved imaging of the nucleus itself. High-resolution imaging could offer direct insights into its size, shape, and surface features, thereby greatly reducing the uncertainties that currently surround mass estimates and thermal models. If these images reveal a nucleus with properties consistent with natural formation, such as normal density and composition, natural explanations become more plausible. Conversely, if imaging uncovers unexpected high density, unusual geometry, or surface features that conflict with natural formation scenarios, the artificial hypothesis would gain increased credibility. The media landscape surrounding 3I Atlas vividly illustrates both the opportunities and the hazards inherent in studying phenomena that may challenge our understanding of natural processes. Some outlets and commentators have already embraced speculative interpretations, sensationalizing headlines about alien probes and interstellar visitors to capture public attention. While such narratives can inspire curiosity and broaden interest, they also risk misleading audiences about the current state of scientific evidence. It is important to emphasize that respected scientific organizations, including NASA and major astronomical institutions, have consistently maintained a cautious stance, emphasizing natural explanations and reaffirming that there is no current evidence of any threat to Earth. Their careful tone reflects a commitment to ongoing research, prioritizing scientific rigor and avoiding premature conclusions while acknowledging the extraordinary nature of the questions at hand. The delicate balance between scientific prudence and public curiosity embodies fundamental questions about how society should navigate discoveries that could reshape our understanding of the universe. Jumping to premature conclusions about artificial origins risks undermining the credibility and funding necessary for legitimate scientific inquiry, potentially stifling progress and casting doubt on future findings. Conversely, an overly cautious stance might cause us to overlook genuine signs of extraterrestrial intelligence, dismissing anomalous signals or objects too swiftly and thus missing vital opportunities for discovery. The key to resolving this tension hinges on sustained, meticulous observation, particularly during the critical window around perihelion, and extending beyond this moment to gather as much data as possible from this rare chance to study an active interstellar visitor up close. Even if in the end, the object, like 3I Atlas, turns out to be a natural phenomenon, its detection has already driven significant advancements in our detection techniques and analytical methods. These improvements will undoubtedly prove invaluable when the next enigmatic visitor arrives armed with better tools and sharper insights. This brings us to the dawn of what can be called the Vera Rubin era, named after the pioneering astronomer whose legacy continues through a groundbreaking project, the Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory situated atop Cerro Pachon in Chile, is poised to revolutionize our grasp of the universe's dynamic nature. Starting in the year 2025, this state-of-the-art facility will capture images of the entire southern sky every 3 nights, reaching depths of observation previously thought impossible. Over the span of a decade, it will generate a detailed, time-lapse record of cosmic evolution, an unprecedented visual chronicle of the universe's ongoing transformation. For the specific pursuit of interstellar object detection, this capability marks a quantum leap forward, promising to multiply discovery rates by orders of magnitude compared to current efforts. At present, our ability to detect interstellar visitors depends heavily on luck and the dedicated efforts of existing surveys such as ATLAS, LINRAI, and the Catalina Sky Survey. While these programs have demonstrated remarkable success in identifying unusual objects, their sensitivity thresholds and limited sky coverage mean that many faint, fast-moving interstellar wanderers likely slip past unnoticed. The Rubin Observatory's combination of expansive field coverage, substantial depth of limiting magnitude, and rapid observational cadence will dramatically enhance our capacity to catch these fleeting visitors as they traverse our neighborhood, often only briefly. To put this into perspective, current surveys detect roughly 1 interstellar object every few years, a sample too small for robust statistical analysis of their properties or behaviors. Rubin's projections suggest that once fully operational, the survey could identify dozens of such objects annually, amassing a rich data set capable of distinguishing natural variations from truly anomalous phenomena. This increase in detection frequency is not merely a matter of numbers. It fundamentally transforms the scope and depth of our research. Early identification of interstellar visitors, months or even years before their closest approach, will provide critical lead time for comprehensive follow-up studies. With such extended planning horizons, astronomers can orchestrate coordinate campaigns involving the world's most powerful telescopes, conducting detailed spectroscopic analyses, precise astrometric measurements, and even preparing potential spacecraft missions. These efforts will be vastly more effective than the hurried, often limited observations that characterized our initial responses to objects like Oumuamua and 3 Atlas, allowing us to extract maximum scientific value from each encounter. In this way, the Vera Rubin Observatory's ambitious survey program promises not just to increase the number of discoveries, but to elevate the quality and depth of our understanding of these mysterious interstellar visitors. The process of transitioning from the initial detection of an interstellar object to its detailed characterization presents a formidable logistical challenge that will necessitate unprecedented levels of global coordination among astronomers and space agencies. Modern automated detection systems must sift through millions of nightly observations, swiftly flagging potential interstellar visitors and triggering immediate alerts to follow-up networks equipped with specialized instruments. These follow-up facilities, designed for rapid spectroscopy and high-precision astrometry, are crucial for capturing fleeting moments of activity and deciphering the object's fundamental properties before it slips away into the cosmic background. This capability for real-time analysis marks a significant departure from the practices of previous decades, when discoveries often remained unrecognized or unconfirmed until weeks or even months after the initial sighting. Such delays meant that vital early data were frequently lost, limiting our understanding of these transient visitors. Now, however, the ability to respond instantly transforms our approach, enabling us to gather a comprehensive set of observations during the critical window when the object is most accessible and active. As sample sizes increase from isolated cases to larger populations, the scope for statistical analysis expands dramatically. Questions that once seemed speculative, such as whether objects like 3I Atlas with its CO2-dominated spectrum are typical or exceptional among interstellar objects, can now be addressed with greater confidence. Do most interstellar visitors exhibit the familiar cometary behaviors observed in objects like Borisov? Or are anomalies more common than our limited sample suggests? To answer such questions definitively, we need dozens, if not hundreds, of well-characterized objects. The implications of these findings are profound for SETI research. The rate at which we discover and analyze interstellar objects directly influences our understanding of their nature and origin. If even a small percentage of these visitors turn out to be artificial constructs, perhaps probes or remnants of extraterrestrial technology, then rapid detection and comprehensive analysis could provide the first confirmed evidence of non-terrestrial engineering. Conversely, if extensive surveys reveal that all interstellar objects conform to natural physical laws and compositions, this would impose crucial constraints on the prevalence of extraterrestrial civilizations and the likelihood of detecting their technosignatures through indirect means. It would also refine our detection strategies, focusing efforts on understanding natural processes rather than searching for artificial anomalies. Looking ahead, mission feasibility studies for intercepting interstellar objects become increasingly practical when planners have years, rather than months, of warning. Small, dedicated spacecraft could be launched to rendezvous with particularly intriguing objects, enabling in situ measurements that are impossible from ground-based telescopes. Although such missions demand rapid development, streamlined launch capabilities, and precise navigation, the potential scientific gains, such as directly sampling interstellar material, could justify these efforts, offering insights into the composition, structure, and possibly even artificial features of these visitors. The Vera Rubin Observatory promises to revolutionize this field by revealing whether objects like 3I Atlas are rare anomalies or representative of a broader yet undetected population. Should similar objects with unusual chemical signatures and unexpected dynamics be observed regularly, it would suggest that our current models of comet physics require substantial revision. On the other hand, if 3I Atlas remains a unique case among a growing roster of well-characterized interstellar objects, its peculiarities could point toward non-natural origins, sparking new hypotheses about extraterrestrial influence or engineering. Furthermore, the increasing frequency of discoveries offers valuable opportunities for education and public engagement. The media excitement surrounding interstellar visitors such as Oumuamua and 3I Atlas demonstrates a potent public fascination with these cosmic messengers. By maintaining a steady stream of findings, the scientific community can foster sustained interest in astronomy and planetary science, inspiring new generations of researchers. When new objects are detected frequently enough, this engagement can be sustained without overwhelming audiences with complex technical details, creating a broader cultural appreciation for our ongoing exploration of the cosmos. The importance of global collaboration in advancing our understanding of interstellar objects cannot be overstated, especially given the rapidly increasing rate at which such visitors are being detected. No single nation's telescope infrastructure alone suffices to carry out the comprehensive follow-up observations necessary to study dozens of these cosmic travelers each year. To truly capitalize on these fleeting opportunities, a coordinated international effort is essential, one that involves sharing observational time, data, and analytical expertise across borders and institutions. Such a collective approach will facilitate a transition from viewing each interstellar object as an isolated puzzle to understanding them as part of a broader population. This shift will fundamentally alter how scientists analyze and interpret these objects. Instead of treating every discovery as a unique anomaly requiring bespoke solutions, researchers will develop standardized rapid response analysis pipelines. These tools will enable swift differentiation between natural phenomena, typical variations expected among comets, and truly extraordinary objects that could warrant deeper investigation or even challenge existing paradigms. Regardless of what the upcoming Vera Rubin Observatory's survey might reveal about the frequency of unusual interstellar visitors, the current enigma surrounding 3I Atlas demands a resolution rooted solely in the evidence it offers. Months of intensive observation, coupled with detailed spectroscopic analysis and orbital modeling, have produced a compelling case study illustrating how science confronts phenomena that seem to stretch or defy established theories. Such phenomena compel us to maintain a healthy skepticism, recognizing the extraordinary claims while rigorously testing their validity. This leads us to the central question that has driven this entire investigation. What exactly is 3I Atlas? The data accumulated through some of the most advanced astronomical instruments available paints a picture that is complex and resistant to simple classification. It offers tantalizing clues pointing in multiple directions, yet none of these clues provide definitive confirmation of its true nature. The mainstream scientific community, including organizations like NASA, tends to favor a naturalistic explanation. From this perspective, 3I Atlas appears as an interstellar comet with unusual but not impossible characteristics, explainable through known natural processes operating under extraordinary or exotic conditions. Its chemistry, notably its richness in carbon dioxide, suggests that it may have formed near a CO2 ice line in its parent stellar system, possibly around a star of a different type than our Sun, or within a protoplanetary disk characterized by unusual chemical gradients, unlike those that shaped our solar system's architecture. Furthermore, the detailed observations of its coma and tail, carefully captured by both the Hubble Space Telescope and ground-based observatories, demonstrate classic comet behavior. These structures respond predictably to solar heating and radiation pressure, following established patterns observed in our solar system's comets under specific geometric alignments. The observed transition from the object's unusual anti-tail features to the formation of a conventional dust tail aligns with well-understood processes, reinforcing the view that the object's activity can be explained through known physics. Additionally, the observed increase in the production of nickel and cyanide molecules as the object nears perihelion matches theoretical models predicting heightened sublimation rates due to increasing solar flux. Most critically, the apparent absence or extremely low magnitude of non-gravitational acceleration can also be comprehensively explained by natural mechanisms without invoking exotic physics or artificial intervention. These findings collectively support a natural origin hypothesis, emphasizing that the phenomena observed are consistent with known cometary physics, albeit at the extreme edge of current understanding. If the hypothesis that 3I Atlas harbors an extraordinarily high mass, estimated by some analyses to be around 3 1/3 times 10 to the 10th metric tons, proves accurate, then the conventional understanding of outgassing-driven propulsion encounters a fundamental obstacle. Under normal circumstances, the force generated by the sublimation of gases from an active comet's surface, known as outgassing, provides a measurable thrust that can subtly alter its trajectory. However, such an immense mass would require an implausibly large amount of thrust to produce any significant deviation, rendering natural outgassing insufficient to produce the observed effects. In other words, the typical force generated by sublimating materials would simply be too weak to cause noticeable deflections in an object of this magnitude. Alternatively, if we consider that the surface composition and rotation dynamics of 3I Atlas lead to remarkably symmetric outgassing patterns, then the apparent contradiction can be explained without invoking new physics or unknown materials. In this scenario, individual jets of sublimating gases are arranged or distributed in such a way that their momentum vectors effectively cancel each other out. As a result, despite active outgassing, the overall thrust in any particular direction remains minimal or even negligible, while the object continues to display spectacular visual phenomena, such as bright plumes or evolving tails, due to the localized activity. This explanation relies solely on known physical principles, requiring no revolutionary theories or exotic formation scenarios. It aligns with the vast diversity of objects found in interstellar space, which exhibit a wide range of compositions, thermal histories, and structural properties. Such diversity reflects the myriad stellar systems and planetary formation processes across our galaxy. Therefore, 3I Atlas, with its unusual characteristics, can be viewed as representing the extreme, yet naturally occurring tail end of this distribution rather than serving as evidence of artificial construction. A more speculative but increasingly discussed perspective, most notably championed by researchers like astrophysicist Abraham Loeb, argues that these anomalies, when considered collectively, resist a purely natural explanation. While each individual trait might be dismissed as an extraordinary, yet plausible natural anomaly, the convergence of multiple unusual features in a single object approaches a statistical improbability that prompts consideration of artificial origins. For instance, the persistent absence of detectable non-gravitational acceleration, despite clear signs of asymmetric outgassing, could be explained by active stabilization systems akin to artificial thrusters. These could include miniature reaction control thrusters or other forms of cold gas microthrusters which would precisely counteract natural thrust vectors. Such systems could maintain the object's trajectory stability while still allowing for controlled emission of material, perhaps for reconnaissance or other purposes. The existence of such technology is well within the realm of human engineering. The question then arises, could some advanced extraterrestrial civilization have developed such capabilities at interstellar scales? If so, they might deploy autonomous probes or craft equipped with these stabilization and emission systems to explore distant star systems discreetly. Adding weight to this line of speculation is the peculiar chemical signature observed in 3I Atlas, particularly the detection of nickel without accompanying iron. While the nickel signature could be explained through natural space weathering processes, where cosmic rays, solar wind, or other factors selectively alter surface materials, the pattern also closely matches the erosion signatures expected from high-temperature nickel-based superalloys used in advanced propulsion technology. If 3I Atlas is a reconnaissance probe experiencing operational wear, the spectroscopic evidence might be capturing this degradation process in real time, suggesting an artificial origin. Furthermore, the apparent mass concentration inferred from outgassing analysis could reflect construction designed for durability and long-term interstellar travel rather than a naturally assembled body. Objects that are purpose-built rather than formed through natural accretion might attain densities and structural properties that are impossible for typical planetesimals, which form via gravitational collapse and collision processes. Even the trajectory characteristics of 3I Atlas have prompted intriguing speculation. Some analyses suggest that its path has been deliberately navigated to optimize specific objectives, such as maximizing solar energy collection, maintaining particular orientations relative to the ecliptic plane, or enabling extended observational windows. Such deliberate course adjustments would imply a level of purposeful control that transcends natural orbital mechanics, hinting at an artificial agenda designed for reconnaissance, observation, or communication. In sum, these converging lines of evidence, ranging from its extraordinary mass estimates and chemical peculiarities to its navigational patterns, raise profound questions. Are we witnessing an artifact of alien engineering, or simply an extraordinary natural object operating within the bounds of known physics? The current debate remains open, but the possibility that advanced technological civilizations might deploy stable, self-stabilizing probes capable of long-distance interstellar reconnaissance continues to gain serious scientific consideration. While these observed patterns could merely align with natural orbital mechanics, there remains a possibility they also hint at deliberate course adjustments executed with a precision that currently exceeds human technological capabilities. In scientific inquiry, the standards of evidence necessary to accept an artificial origin are inherently more rigorous than those required to explain phenomena through natural processes. At present, the data we possess falls short of these elevated thresholds. Indeed, extraordinary claims such as the existence of non-terrestrial technology necessitate extraordinary evidence. As it stands, the anomalies presented by 3I Atlas are compelling and intriguing, yet they do not constitute definitive proof of extraterrestrial origin. Each of these unusual characteristics can be interpreted through natural explanations, which, although they might depend on specific or coincidental conditions, still fall within the boundaries of known physical laws and processes. However, the core of scientific integrity demands that we approach such phenomena with intellectual honesty, acknowledging the limitations of our current theoretical frameworks. Our present understanding of comet physics, for example, is primarily derived from objects within our solar system, formed under well-studied environmental conditions, specific ranges of temperature, pressure, and chemical makeup. These models serve well for familiar objects, but interstellar visitors arrive from environments that may operate under entirely different rules. Their origins, compositions, and behaviors could deviate significantly from what our local models predict, presenting a fundamental challenge to our ability to accurately forecast their dynamics. The line between classifying an object as a cosmic anomaly or an alien artifact may ultimately hinge on factors beyond our observational reach during the current apparition of 3I Atlas. As scientific tools and theories improve, through future discoveries of similar objects, refined models that better account for exotic cometary behaviors, or enhanced detection techniques capable of identifying artificial materials, the balance of evidence could shift. Such advancements might either bolster the natural explanation or lend weight to the hypothesis of artificial origin. For now, we are left in a state of genuine uncertainty. We encounter phenomena that push the boundaries of our established scientific understanding, but stop short of definitive confirmation of anything extraordinary. This state of ambiguity is emblematic of frontier research. It reflects a natural condition where the most compelling questions often resist immediate answers. Addressing these mysteries demands patience, perseverance, and a willingness to maintain intellectual humility, recognizing that our current models are incomplete and that the truth may be more complex than our present theories suggest. The ultimate resolution may not come solely from the study of 3I Atlas itself, but from the broader context of future interstellar visitors and the increasingly advanced observational capabilities that will define the next era of cosmic reconnaissance. This leads us to consider the so-called masked broadcast theory, a fascinating idea proposing that what we interpret as anomalies might in fact be intentional signals encoded within the object's physical characteristics. Imagine, for instance, that instead of questioning why 3I Atlas exhibits activity without noticeable acceleration, We consider whether an advanced civilization might have engineered such precise behavior deliberately. The masked broadcast concept, emerging from the intersection of SETI research and sophisticated signal processing theories, suggests that 3i Atlas might not be trying to conceal its artificial nature. Rather, it could be transmitting a message, using the most universal language available to any species proficient in chemistry. This speculative framework reinterprets what we see as anomalies, framing them as elements of intentional design rather than mere natural phenomena. In this view, the apparent lack of non-gravitational acceleration amidst observable outgassing is not an absence but a feature, possibly an engineered characteristic aimed at conveying information. Such a hypothesis challenges us to think differently about the signals that interstellar objects might carry, emphasizing that they could be crafted to communicate rather than conceal. While this idea remains speculative, it opens new avenues of inquiry, prompting us to consider that some interstellar visitors may be more than just cosmic wanderers. They could be carriers of messages encoded in the very physics and chemistry that we observe. Despite an apparent lack of measurable non-gravitational acceleration, vigorous outgassing from this interstellar visitor could serve as the foundation for a subtle, low-bandwidth communication system, one that assumes intelligent civilizations will direct their most advanced instruments toward such anomalies. Any species capable of detailed spectroscopy would likely detect embedded modulation patterns within the natural chemical signatures of the comet's coma, effectively creating a universal messaging channel that requires no prior understanding of alien languages or technological conventions. From a cosmic vantage point, the elegance of this mechanism becomes strikingly clear. Spectral lines, those specific wavelengths at which atoms and molecules emit or absorb light, are governed by fundamental physical constants that remain invariant across all known technological civilizations. For example, hydrogen naturally emits photons at a wavelength of 21 centimeters, a fact that holds true whether observed by human radio telescopes or by hypothetical extraterrestrial observatories. Similarly, absorption features associated with carbon dioxide occur at the same characteristic frequencies regardless of the observer's species, terrestrial or alien. This universality provides a common language rooted in the laws of physics, one that any technologically capable civilization could interpret. A modulation scheme could be constructed on ratios of these spectral signatures. Variations in the relative abundance of molecules like carbon dioxide and water vapor, fluctuations in the strength of nickel emission lines, or subtle shifts in isotopic signatures, each serving as a form of coded information. Such signals, operating through what signal processing experts call amplitude modulation, would alter the intensity of specific chemical emissions in a controlled, deliberate manner. These minute, time-varying patterns could be detected by any civilization equipped with high-precision spectroscopy, as the overall outgassing remains symmetric enough to preserve the object's stable trajectory, yet subtly varies at the chemical level. This symmetry in outgassing maintains the object's orbit predominantly under gravitational influence, with the spectral signatures telling a different story, one that cannot be explained by natural physics alone. Over months of spectral data collection, complex encoding grammar could be embedded within these chemical variations. For instance, the timing of certain intensity fluctuations might follow prime number sequences, patterns that would immediately signal an artificial origin to any civilization familiar with advanced mathematics. Alternately, ratios of line strengths, such as Fibonacci progressions, could serve as confirmatory indicators of intentional design, distinguishing deliberate signals from random natural processes. Furthermore, references to universal constants, like the hyperfine transition period of hydrogen, the fine structure constant, or fundamental mathematical ratios such as pi, could act as cosmic Rosetta Stones bridging the vast evolutionary and spatial divides between civilizations. The peculiar nickel emission signature, notably absent or weak in natural comet chemistry where iron would typically be present, might take on new significance within this context. If natural processes produce both elements together, then a deliberate enhancement of nickel emissions, controlled and tiny, could function as an interstellar Morse code, with the absence or reduced presence of iron emphasizing the intentional nature of the modulation. In this scenario, minute, precisely calibrated variations in nickel line intensity would serve as the dots and dashes of an interstellar communication, while the anti-tail geometry observed during the early approach phase could act as punctuation, marking boundaries between symbol groups or segments within the encoded message. Such an approach would be highly subtle, designed to blend seamlessly with natural outgassing phenomena, while embedding a deliberate message accessible to any sufficiently advanced spectroscopy-based civilization, revealing a sophisticated method of interstellar communication hidden within the very chemistry of an unassuming comet. As the orbital motion of the object causes the viewing angles to shift, different segments of its expansive dust and gas coma gradually come into view. This dynamic change naturally introduces discernible breaks and variations within the observational data, offering critical clues that can help distinguish potential embedded signals or deliberate messages from the persistent background chemistry, typical of such celestial bodies. Even the initial surge in brightness that first drew astronomical attention takes on a new, more intriguing interpretation, possibly as an intentional greeting or tone burst, carefully timed to ensure early detection and facilitate comprehensive analysis. If an extraterrestrial civilization intended to maximize the effectiveness of their encoded message, they would likely plan their signal to be detectable well before the object reaches its perihelion, the point of closest approach to the Sun, when natural activity levels tend to peak. During this period, the intense sublimation of volatiles and the resultant outgassing could drown out or obscure subtle artificial modulations, blending them into the overwhelming background noise of natural cometary processes. To decode such a message, scientists would need to undertake a meticulous systematic examination of all available spectroscopic and photometric data collected throughout the entire observable apparition of the object, covering the full span of its visibility. This comprehensive analysis would involve constructing detailed time series from the published spectra, carefully normalizing the data to account for natural variations caused by changing phase angles, shifts in the heliocentric distance, and potential rotation periods of the body itself. The core challenge lies in distinguishing genuine artificial signals from the myriad natural drivers, such as thermal effects, outgassing patterns, and observational biases that could produce spurious periodicities or apparent anomalies. Researchers would seek residual patterns that stubbornly resist explanation within the framework of known astrophysical physics, focusing their attention on signatures like non-astrophysical periodicities, prime-numbered intervals in emission line intensities, or irrational ratios in beats between different chemical species, phenomena unlikely to originate from natural processes. To enhance this search, modern signal processing techniques, originally developed to extract weak radio signals from the noisy cosmic background, could be adapted to analyze spectroscopic datasets. These advanced methods would help identify subtle artificial patterns that might be concealed within the complex spectral information. Visual tools such as spectrograms could be employed, highlighting periodic beats in emission lines over time. Subsequent statistical analyses could then generate grid-like representations, revealing prime number spacing or other structured regularities that withstand rigorous significance testing. If genuine non-natural cadences or signatures were embedded within the data, they would likely generate headlines across scientific journals worldwide, prompting unprecedented levels of international collaboration aimed at deciphering the message. Such a discovery would carry profound implications for our understanding of extraterrestrial intelligence. However, critical skepticism remains essential. Natural coma variability, instrumental observing cadences, and observational gaps can all produce patterns that mimic artificial signals, risking false positives. Complex three-dimensional gas flows and chemical interactions within the coma can generate seemingly systematic variations that algorithms, designed to detect order amid chaos, might misinterpret as intentional. Therefore, any claims of detecting artificial modulation would need to be accompanied by statistical significance levels, far exceeding standard astronomical thresholds, ensuring that the pattern is not a coincidental artifact of natural variability. Independent confirmation from multiple observation teams, employing different instruments and analytical methods, would be crucial to validate such a remarkable finding. Ultimately, if the object truly contains an encoded message, the strength and clarity of that signal should vary predictably with the viewing geometry and the object's distance from the Sun, aligning with expectations of how such a deliberate signal might behave under different observational conditions. As interstellar objects draw nearer to perihelion, their natural chemical activity tends to intensify markedly, often producing a dazzling array of outgassing and tail formations. This heightened activity can pose a significant challenge for detecting subtle artificial modulations embedded within their spectra, as the increasing background noise from natural processes risks overshadowing any faint signals that might carry encoded messages. However, this same surge in gas production could potentially work to our advantage. By amplifying the overall signal strength, it might enhance the ratio of artificial pattern signatures against the noisy backdrop, thereby making it easier for us to identify deliberate signals during these peak periods of activity. The scientific community anticipates that specific windows of observation, timed to align with predicted phases of heightened activity, could maximize our chances of detecting artificial communications. These optimal periods are not random but are expected to coincide with particular geometric configurations. For instance, the angles at which we observe features like the anti-tail, material that appears to point sunward rather than away, may also be ideal for capturing any embedded signals within the comet's chemistry. By meticulously scheduling spectroscopic campaigns to occur precisely during these windows, researchers could conduct targeted investigations capable of conclusively determining whether anomalous patterns exist within the chemical emissions of the object. Achieving such a comprehensive search, however, necessitates unprecedented levels of global coordination. No single observatory holds the continuous wide-ranging coverage required to monitor the entire apparition with sufficient resolution and temporal persistence. Instead, an integrated network of observatories must collaborate, sharing data and aligning their observing schedules. This effort would involve establishing standardized data reduction procedures and analysis protocols, ensuring that measurements from different telescopes, spread across various time zones and operating at diverse wavelengths, can be seamlessly combined. Only through such collaborative synergy can we hope to piece together a coherent picture of the chemical signals and identify potential artificial patterns. The stakes of success in such an endeavor would be nothing short of transformative. Confirming the existence of artificial signals originating from an interstellar visitor would serve as incontrovertible evidence that technological intelligences exist beyond our solar system, capable of engineering signals that traverse cosmic distances. Such a discovery would not only validate the possibility of extraterrestrial communication, but also reveal the methods and complexities involved in transmitting information across vastly different evolutionary and technological contexts. The content of these messages could range from advanced scientific knowledge to philosophical insights, or practical details about the cosmic environment that surrounds our solar system. Even if these searches yield no positive detections, the effort would still produce invaluable scientific insights. Null results would impose critical constraints on the kinds of communication strategies extraterrestrial civilizations might employ, refining our understanding of what is plausible and what remains beyond our detection capabilities. They would also serve to validate and improve our models of natural chemical processes in interstellar comets, sharpening our ability to distinguish between natural phenomena and potential artificial signatures. The development and refinement of these search methodologies will prove increasingly vital as survey programs like the Vera Rubin Observatory ramp up their discovery rates, potentially identifying dozens or even hundreds of interstellar objects passing through our cosmic neighborhood. The masked broadcast theory, a concept that posits civilizations might deliberately embed messages within the chemical signatures of their objects, embodies the kind of bold scientific speculation that drives progress. This hypothesis suggests that the absence of overt signals does not preclude the existence of embedded communication, but rather invites us to look more carefully at the subtle, encoded patterns woven into the spectra. Whether this theory ultimately turns out to be correct, or leads us astray down intriguing but false trails, the very act of considering such possibilities exemplifies the scientific courage necessary to push the boundaries of our understanding. It encourages us to challenge our deepest assumptions about intelligence, communication, and our place in a universe that may be far richer, more complex, and more populated than we currently imagine. In this pursuit, even the pursuit of false leads is valuable, for it expands our horizons, sharpens our tools, and prepares us for the profound discoveries that await. If the enigmatic three-eye atlas indeed conceals an encoded message, it might signal only the initial phase of a far more intricate and far-reaching infiltration strategy, one designed to subtly seed our solar system with countless tiny technologies that evade detection by traditional astronomical means. Imagine then a scenario far more sophisticated than we have previously envisioned, one encapsulated within what could be called the decoy shepherd strategy, centered around minuscule probes hidden within cosmic dust. This concept draws inspiration from the most advanced military tactics, where decoys and diversions are employed to divert enemy attention while the real operation proceeds stealthily along parallel pathways. Applied to the domain of interstellar reconnaissance, this idea suggests a chilling possibility: that the conspicuous object we observe, Three-Eye Atlas, is not the true focus of an alien mission but rather a strategic distraction, a smokescreen designed to occupy our telescopes and observational efforts while the genuine payload achieves its objectives through entirely different covert means. In this framework, the decoy shepherd scenario posits that Three-Eye Atlas functions more like a cosmic school bus than a solitary explorer. Its primary task might be to drift innocuously through our inner solar system, all the while quietly dispersing a multitude of microscopic probes, ranging in size from millimeters to centimeters, disguised convincingly as ordinary cometary dust. These tiny payloads could then spiral into carefully chosen regions within our solar system. Earth Trojan points, the far side of the moon's craters or layers within our upper atmosphere, areas where they could carry out long-term surveillance and reconnaissance operations. Crucially, these microprobes would be engineered with such remarkable subtlety that their presence would remain undetectable using current conventional detection methods. Their minuscule size, combined with advanced stealth capabilities, would allow them to blend seamlessly into the natural environment of cosmic dust and debris. By dispersing these tiny units into strategic niches, an advanced civilization could maintain a persistent, covert observational network, quietly gathering intelligence without attracting attention. The engineering demands for such a strategy help explain every oddity and anomaly we've observed in the behavior of Three-Eye Atlas. an object that, despite its activity, appears to resist the expected dynamical effects of outgassing and propulsion. To maintain precise control over such a swarm of microprobes, the parent object would need to achieve trajectory stability with near-zero net non-gravitational acceleration. This would ensure a predictable and accurate deployment process. Any asymmetry in outgassing, if it were to occur, would scatter the probes in unpredictable directions, undermining the entire infiltration effort. Therefore, the system would require a form of symmetric outgassing that cancels thrust vectors while still allowing vigorous activity on the parent body, thus maintaining the illusion of natural cometary behavior. This symmetry serves a dual purpose. On one hand, it provides the perfect cover story. Most scientists would interpret such activity as natural outgassing, consistent with the physics of comets, and thus dismiss any suspicion. On the other hand, it establishes a stable platform for the controlled release of these artificial microprobes at predetermined locations and times, enabling a highly organized covert surveillance network. From an observational standpoint, the visible coma and tail, those familiar features of cometary activity, would serve as the ideal camouflage for deploying these microprobes. Since the environment created by dust and gas emission resembles what we expect from natural comets, it would be virtually impossible for our current instruments to distinguish between routine dust particles and intentionally released artificial probes. Most such tiny units would be indistinguishable from the ordinary dust liberated by solar heating of volatiles, making their detection exceedingly difficult. However, a keen observer, one monitoring meteor databases or wide-field imaging surveys, might still detect subtle anomalies. These could manifest as unusually coherent streams of particles, exhibiting narrow velocity dispersions and specific directional patterns that do not match known meteor showers. Such streams might appear at particular solar longitudes, timing that would not correspond to any natural meteor activity, and could subtly hint at an artificial coordinated dispersal of microprobes. Recognizing these faint signatures would require careful analysis, but their detection could offer compelling evidence of an elaborate covert reconnaissance operation, an invisible network of interstellar sensors silently watching from within the dust of our solar system. Within this context, the peculiar presence of nickel takes on a profoundly ominous tone. It's plausible that tiny nickel-enriched coatings on miniature probes could act as resilient shields, safeguarding these devices against the relentless assault of ultraviolet radiation and cosmic particles during their long journeys across interstellar space. When these probes are eventually exposed to the intense heat of solar radiation upon deployment, perhaps during a targeted operation, they would undergo ablation, shedding layers of material and revealing the distinctive emission lines characteristic of nickel in spectroscopic observations. This process could explain why nickel signatures are so prominently detected, while iron, despite its abundance in many natural materials, remains conspicuously absent below detection thresholds. Essentially, as these microprobes activate, they peel off their protective skins, leaving behind a chemical fingerprint that has puzzled scientists for months. Strategically, the zones chosen for deploying these probes would likely be selected for their maximum operational advantage while minimizing the risk of detection. Locations like Earth-Sun Lagrange points, specifically Lagrange points L4 and L5, offer gravitationally stable regions where objects can linger indefinitely without the need for continuous propulsion or station-keeping efforts. These points serve as natural parking spots, providing ideal vantage points for monitoring Earth's electromagnetic emissions, tracking space traffic, and observing technological developments, all while remaining virtually invisible to ground-based telescopes due to their proximity to the sun's glare. Even more attractive are the permanently shadowed regions within lunar polar craters. These craters maintain extremely low temperatures, making them perfect for preserving delicate electronic systems and sensitive instrumentation over extended periods. The natural shielding offered by the lunar terrain also helps block the radio noise from Earth, creating ideal conditions for covert operations. Probes landed in such secluded spots could operate as silent listening posts, establishing direct lines of communication with their originating civilization, all while remaining hidden within the dark hemisphere of the Moon that never faces Earth. Beyond these stable lunar and Earth-associated locations, atmospheric deployment presents another intriguing avenue for active reconnaissance. These microprobes, designed for aerodynamic flight, could utilize Earth's mesospheric layers as temporary staging grounds. By exploiting atmospheric drag, they could fine-tune their orbits and positions during missions, conducting detailed surveys of our planet's atmospheric conditions, chemical makeup, and even infrastructure. Such objects would likely only be visible in meteor radar databases for fleeting moments before vanishing, mimicking the natural appearance of micrometeorites, yet in reality serving as sophisticated surveillance platforms. The timing of such operations would reveal a disturbing level of strategic sophistication, suggesting an intent to blend seamlessly into natural phenomena and avoid detection. The arrival of 3I Atlas coincided with humanity's current peak in observational capability. Instruments like the James Webb Space Telescope, Hubble, and ground-based adaptive optics systems are now capable of detailed characterization of distant objects, their compositions, and behaviors. Simultaneously, the proliferation of small satellites, radar networks, and citizen science initiatives has created an unprecedented and densely packed sensor environment, an intricate web of observational assets that, in principle, could detect the deployment of microprobes if anyone knew where and how to look. This convergence of advanced technology and strategic planning underscores the extraordinary level of effort that might be involved in covert interstellar reconnaissance, raising questions about the extent of alien technological sophistication and intent. A highly cautious yet intriguing line of reasoning suggests that advanced extraterrestrial civilizations might intentionally orchestrate reconnaissance missions to coincide precisely with the phase when a target species, like humanity, is at its most vulnerable and least capable of resistance. This period, often referred to as a species' technological adolescence, is characterized by a window when the civilization has begun exploring space and developing the means to detect distant objects, yet remains too primitive to mount effective defenses or countermeasures against sophisticated probes or surveillance devices. In our current era, humanity is actively expanding our presence in space, deploying satellites, exploring planetary bodies, and even contemplating crewed missions beyond Earth orbit. However, our capabilities for deep space monitoring, particularly in detecting subtle covert activity, are still limited compared to the potential sophistication of an interstellar civilization's reconnaissance systems. This juncture in human history, marked by a burgeoning space footprint but modest detection infrastructure, might represent an optimal moment for an advanced civilization to perform detailed surveys of our world, effectively sampling our technological development before we reach a stage of full awareness or capability to respond. If this paranoid hypothesis holds any validity, then the breadcrumbs of such clandestine activity should already be embedded within various observational datasets accumulated over decades. For instance, meteor radar networks around the globe tirelessly scan the upper atmosphere for natural debris, meteoroids, cataloging their velocities, trajectories, and chemical compositions. Should a microprobe or a swarm of tiny artificial particles have been deployed deliberately, certain anomalous streams, small, fleeting clusters of particles, might trace back to the position of objects like 3I Atlas during specific, narrowly defined time windows. These streams could act as telltale signatures, evidence of a deliberate deployment event by an intelligent agent. Similarly, wide-field astronomical surveys, initially designed to hunt for asteroids and comets, maintain extensive archives of transient detections. These catalogs may contain brief, point-like sources appearing suddenly and vanishing just as quickly. Phenomena that could correspond to microprobes adjusting their positions, deploying sensors, or temporarily increasing their brightness to gather data. Such signals, appearing over days or weeks in regions like the Earth's Lagrange points, areas where gravitational forces balance to create stable zones, could be the artificial signatures of surveillance devices actively conducting sensor sweeps or repositioning. The citizen science community, comprising amateur astronomers and hobbyist radar enthusiasts, plays a vital role in this search. Amateur radio operators involved in meteor scatter detection, using forward scatter systems, are capable of spotting faint particle streams that escape the reach of professional radar arrays. Likewise, amateur astronomers with wide-field imaging systems can coordinate targeted campaigns during optimal viewing windows, such as around new moon phases, when the background sky is darkest, increasing the likelihood of detecting subtle, transient phenomena. To falsify this decoy shepherd scenario, wherein microprobes are deployed to monitor and possibly manipulate the environment, scientists could systematically analyze existing observational data spanning decades. If the activity were natural, then no coherent, chemically distinctive microstreams should be traceable back to 3I Atlas's position, nor should there be consistent localized detections aligned with the object's hypothesized deployment windows. Furthermore, focused searches around the Earth's Lagrange points, regions known for their gravitational stability, should yield no persistent or statistically significant evidence of artificial objects if no such activity exists. High-resolution imaging techniques could offer a decisive test. Should the object's nucleus be found to be smaller and less massive than required to house and operate a fleet of microprobes, say if its size and mass are inconsistent with carrying significant payloads, then the logistical demands of deploying and maintaining such an artificial swarm become implausible, collapsing the scenario under its own weight. Ultimately, confirming the presence of microprobes or artificial sensor networks would be an extraordinary revelation, with implications that dwarf even the discovery of encoded messages within the coma of 3I Atlas. Such evidence would suggest that the object isn't merely a natural celestial body, but perhaps a deliberately placed or manipulated artifact, an active node in a broader interstellar reconnaissance network. Yet, until such signatures are conclusively identified, the hypothesis remains a tantalizing, if speculative, possibility, one that underscores the importance of meticulous analysis, thorough data mining, and vigilant observation in our ongoing quest to understand what, if anything, might be observing us from the depths of interstellar space. Active monitoring of our solar environment by artificial systems might represent far more than a mere encounter with extraterrestrial intelligence. It could serve as undeniable proof of ongoing deliberate efforts to observe and gather information about us. Such a discovery would have profound implications, fundamentally reshaping our understanding of planetary security and the trajectory of human civilization's development in space. Imagine the detection of even a single well-defined microstream, an organized flow of material containing chemical signatures that mirror the unusual composition of 3I Atlas. The moment such evidence emerges, it would likely trigger emergency sessions among space agencies across the globe, prompting urgent discussions and coordinated responses. More than that, it would dramatically alter humanity's perception of our place in the universe, shifting the narrative from one of cosmic solitude to one of active surveillance by entities capable of interstellar travel. The realization that we are under the watchful eye of non-human intelligences would compel us to reconsider every aspect of our future endeavors in space. ranging from planetary defense strategies to diplomatic protocols that might one day govern potential contact scenarios. Such a revelation would demand a reassessment of our technological, political, and philosophical frameworks, as we grapple with the possibility that we are not alone, and that we may be part of a broader cosmic network of observation and perhaps communication. However, like all extraordinary hypotheses, the decoy shepherd scenario suggesting that what we observe could be a sophisticated ruse requires extraordinary evidence before it can be seriously accepted. The distinction between mere paranoid speculation and a legitimate scientific hypothesis rests on the rigor of the predictions made, the robustness of testing methods employed, and the scientific community's willingness to discard hypotheses that do not withstand empirical scrutiny. Only through systematic, meticulous investigation can we determine whether 3I Atlas is simply a cosmic oddity, an anomalous object worthy of curiosity, or perhaps the vanguard of an intelligence that has been silently watching us for far longer than we have been observing the stars. The upcoming months will be pivotal in testing these speculative frameworks, especially as 3I Atlas approaches perihelion, the point in its orbit closest to the Sun, and begins its retreat back toward interstellar space. Whether this object leaves behind only scientific papers and contentious theories or tangible evidence of technology that fundamentally alters our understanding of intelligence in the cosmos will depend heavily on how carefully we analyze the subtle traces it leaves behind, be they in the form of signals, chemical signatures, or other detectable phenomena, within the databases and detection networks that record humanity's earliest steps toward becoming a spacefaring civilization. In these final reflections, 3I Atlas compels us to confront a core paradox at the heart of astrophysics and planetary science. Here is an object exhibiting vigorous activity, outgassing, tail evolution, and increasing chemical production, yet producing virtually no measurable acceleration according to the most precise astrometric measurements that underpin our current understanding of orbital mechanics. This apparent contradiction, visible cause paired with an absence of effect, either highlights a significant gap in our theoretical models or suggests that phenomena beyond the scope of conventional physics are at play. The prevailing scientific perspective currently classifies 3I Atlas as a natural object, albeit one existing at the extreme edge of what our observations and theories have previously accounted for. It challenges us to refine our models, to explore the limits of our understanding, and to consider the possibility that the universe still holds many surprises, phenomena that might operate outside the boundaries of standard physics, yet remain consistent with natural processes. Whether it is an extraordinary anomaly or a sign of something more profound, 3I Atlas stands as a testament to the ongoing mystery and wonder inherent in our quest to decipher the cosmos. This interstellar visitor bears the chemical signatures of an origin distinct from that of our solar system, offering clues from a formation environment unlike any we have previously encountered. Its composition is notably unusual, being dominated by carbon dioxide rather than water, a stark contrast to the typical volatile makeup of most comets within our own planetary neighborhood. Adding to the enigma is the peculiar pattern of metal emission observed, a mysterious abundance of nickel in the absence of iron, which defies the expectations set by conventional models of how metals evaporate and emit from cometary nuclei. The apparent mass, the distribution of material, and the symmetry of its outgassing patterns provide plausible natural explanations for the phenomenon of missing non-gravitational acceleration, the subtle forces that should have been detectable if outgassing was exerting a measurable push on the object. These factors, taken together, help to rationalize why the object behaves as it does within the framework of current physics, capturing the attention of scientists across the globe. Yet amid this complex puzzle, it is vital to recognize the role of curiosity-driven anomaly hunting that propels scientific progress. Even if future observations ultimately confirm a natural origin for this object, the insights gained from studying it have already expanded our understanding of what comets, and perhaps other small bodies, can be. The discovery has prompted significant advancements in theoretical modeling, observational techniques, and analytical methods, all of which will benefit not only the study of similar objects within our solar system but also the broader realm of interstellar phenomena. This extraordinary case has demonstrated the immense value of rapid response observational campaigns and the importance of international collaboration. Coordinated efforts enable us to extract the maximum scientific return from brief but critical encounters with interstellar visitors, opportunities that, due to their fleeting nature, demand swift and concerted effort. Beyond the scientific realm, the impact of this discovery reaches into the educational and cultural spheres, inspiring curiosity and wonder among the public at large. In many ways, 3I Atlas exemplifies how authentic scientific inquiry operates at the very edges of our current knowledge. It highlights the delicate balance between embracing the excitement of potential groundbreaking discoveries and maintaining a healthy skepticism, an approach that fosters progress while upholding rigorous standards of evidence and proof. The object serves as a compelling case study in how science navigates the frontier of the unknown, where uncertainty and speculation are essential components of discovery. Looking ahead to the immediate future, the upcoming perihelion passage scheduled for late October of the year 2025 represents the final, perhaps decisive opportunity to resolve the core mysteries that shroud this enigmatic object. As it approaches the Sun, increased solar heating may trigger new activity patterns, perhaps leading to the emergence of detectable acceleration signatures that would confirm natural explanations through direct observation of the rocket effect in action. Conversely, if the object continues to exhibit persistent dynamical stability despite heightened outgassing, it would deepen the mystery and lend weight to more exotic, potentially artificial hypotheses. Spacecraft observations from Mars orbiters and other deep space missions could provide vantage points impossible to attain from Earth-based telescopes. High-resolution imaging during this critical window might finally resolve the nucleus itself, removing uncertainties about its size, shape, and surface characteristics, key factors in differentiating between natural and artificial models. Additionally, precision spectroscopic analysis during the peak of activity could reveal isotopic signatures that serve as definitive markers, helping to distinguish between natural materials formed through cosmic processes and those that might suggest artificial origin. The implications of these findings extend far beyond this single object. They touch upon fundamental questions regarding the prevalence of life and intelligence in the universe. Whether revealing natural phenomena at the limits of our understanding or hinting at the presence of extraterrestrial technology, the study of 3I Atlas could influence our perspective on cosmic life, the nature of technological civilizations, and our place within the broader universe. If the ultimate conclusion about 3I Atlas is that it is a naturally occurring object, this discovery would significantly expand our catalog of cosmic phenomena that, while extraordinary, still function within the boundaries of established physical laws. Such a finding would challenge us to refine our understanding of how natural processes operate under conditions perhaps far beyond our current models. It would serve as a reminder that the universe often reveals complexities that stretch the limits of our predictive capabilities, urging us to develop more sophisticated theories and observational tools to better comprehend these phenomena. Conversely, if subsequent evidence points toward an artificial origin, this would represent one of the most transformative discoveries in human history. Confirming the existence of extraterrestrial technological civilizations would revolutionize our understanding of our place in the cosmos, signaling that we are not alone in possessing advanced intelligence and engineering capabilities. In this context, the statistical significance of such a finding becomes paramount. The fact that we have confirmed just 3 interstellar objects over a span of only 8 years, with 2 exhibiting highly unusual and perplexing characteristics, raises profound questions. Are these anomalies mere coincidences, or do they hint at fundamental differences between objects born within our solar system and those originating from interstellar space? The upcoming era ushered in by the Vera Rubin Observatory promises to transform this tiny sample into a rich data set capable of revealing whether these strange behaviors are rare exceptions or indicative of a broader class of interstellar travelers. As it begins to catalog a far greater number of such objects, patterns, whether natural or artificial, may emerge, helping us distinguish between random anomalies and systematic traits. Achieving this understanding will require unprecedented international cooperation and technological progress. The fleeting windows during which interstellar objects are visible demand rapid detection, immediate spectroscopic follow-up, and real-time data analysis, capabilities that currently push the limits of our observational infrastructure. Success in this endeavor hinges on sustained investment in advanced detection systems, sophisticated analysis methods, and refined theoretical frameworks. These tools must be capable of differentiating between natural variability and phenomena that genuinely challenge our understanding of physics. Perhaps most crucially, 3i Atlas and its successors serve as humbling reminders that the universe continually retains the power to surprise us. Despite centuries of diligent astronomical observation and decades of sophisticated space missions, we persistently encounter objects and phenomena that defy our current models. These encounters compel us to expand our conception of what is physically possible and to remain open to new paradigms. This necessity for ongoing humility and adaptability in scientific inquiry underscores the importance of maintaining an open, questioning mindset, one that recognizes that our knowledge is provisional and that discovery often requires us to question assumptions and refine our understanding. Whether 3i Atlas ultimately turns out to be a natural oddity or an artifact of extraterrestrial intelligence, it has already secured its place as the most significant interstellar visitor since the discoveries of Oumuamua and Borisov. Not because it provides definitive answers to our deepest questions about life and intelligence in the universe, but because it compels us to ask better questions, develop more advanced tools, and uphold rigorous standards for evaluating evidence. This ongoing journey of exploration and discovery continues to challenge and expand our understanding of the cosmos. As observations deepen and our analytical methods improve, we are drawn ever closer to probing the very nature of reality itself. Ultimately, the process of investigating these mysterious cosmic messengers may prove more valuable than any single answer we might uncover, driving us to continually refine our knowledge, broaden our horizons, and reconsider our most fundamental assumptions about the universe we inhabit.